James Webb just stared deeper into the infant universe, and the numbers don't add up. Galaxies appear too massive, too bright, too early, like the cosmos built skyscrapers before it laid the foundation. So are we witnessing real cracks in the standard model, or have we been misreading the oldest light and the true scale of space itself? The universe has never been short on silence, only on certainty. With new James Webb data, that certainty is starting to thin. For a century, cosmology has been a disciplined act of translation, turning faint photons into distances, ages, and origins. We build a coherent history from light stretched across billions of years, then trust the mathematics to hold. But every translation carries assumptions, and assumptions can masquerade as facts when the signal is old enough. James Webb's gift is not simply reach, it is leverage. It doesn't just see farther, it changes what far means by capturing infrared light that once lived in ultraviolet dawn. And when you change the language, you can discover that the story you thought you read was partly invented by your own grammar. This film follows a single, unsettling possibility. The early universe may be forcing a choice between two uncomfortable answers. Either our measurements, our rulers, our clocks, our conversions from brightness to mass are bending in subtle ways, or the universe truly assembled structure with an efficiency our standard picture never budgeted for. To understand the stakes, we have to watch how certainty is manufactured. A redshift becomes a time becomes a distance becomes a mass, then that mass becomes a claim about what the universe is allowed to do. One misstep in that chain can inflate a galaxy, shrink an age, or conjure drama where none exists. Yet if the chain holds, the implications reach beyond any single telescope. We will move through the deep fields where Webb's images look less like a beginning and more like a crowded city at night, then step back to ask what we are actually counting. We will examine the cosmic distance ladder and the standard rulers that anchor it, and we will linger on the tension that refuses to settle when different methods measure expansion and disagree. Because expansion is not background scenery, it is the stage itself. Change the expansion history and you change the time available for everything. Stars, galaxies, black holes, and the chemistry that marks cosmic maturity. What appears too early might be an illusion of calibration, or it might be the universe quietly admitting it runs on rules we have not finished writing. Along the way, we'll confront objects that seem to concentrate mass where it shouldn't gather, engines that shine as if fed by impossible growth, and traces of heavy elements that behave like timestamps stamped into ancient gas. We'll test the ordinary culprits: dust, lensing, selection bias, misidentified spectral breaks, and we'll ask how often the simplest explanation is merely the most familiar. And we'll keep returning to the same haunting lesson. Space is not only enormous in extent, it is enormous in what it can hide. The farther we look, the more the universe demands that we separate what we observe from what we assume, and then decide which of those deserves our faith. By the end, the question will not be whether the cosmos is vast. It will be whether our map of that vastness is finally becoming honest, or finally becoming impossible to defend. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From Webb's infrared window on the first light to the cosmic ruler that measures a moving universe, we'll trace how each inference is made and where it can fail. Then we'll follow the consequences forward to the expansion rate that sets the universe's age and the dark energy that may decide its ending. The first promise of James Webb was simple, almost childlike in its clarity. Point a new eye at the oldest light and watch the first galaxies appear. For decades, cosmology has treated the early universe like a rough draft, an opening paragraph where the ink is still wet. It should be sparse, small, and still assembling itself, because gravity has had so little time to do its work. Webb aimed at the deepest fields and returned something sharper than expected, as if the page already held finished sentences. The images looked crowded, bright, and strangely organized for such an early time, with multiple sources packed into frames that were meant to feel empty. Where we expected tiny clumps fighting gravity, we saw dense structures holding together, and in some cases showing hints of coherent shape. Where we expected faint smudges, we saw luminous systems that seemed already grown, their light strong enough to stand out across the longest distances we can probe. That is the unease at the centre of this story. The infant universe looks, in places, like a later universe, older, heavier, and more settled than the timeline seems to allow. The mission was built for this moment, and the engineering choices reveal the scientific wager. Webb's mirrors and instruments were designed to read light that has been stretched by expansion, shifting the universe's earliest ultraviolet glow into infrared wavelengths we can finally capture. In visible light, the first galaxies are almost ghosts, because their photons have been pulled to longer wavelengths by the swelling of space. In Webb's infrared vision, those same photons arrive as a faint warmth, reddened, shifted, and dimmed by the long growth of the cosmos. Redshift is the key that turns distance into time, but it is also a reminder that space itself is the conveyor belt. The higher the redshift, the farther the light has travelled, and the earlier the snapshot, because the universe was smaller when that light began its journey. At redshifts around 10 to 15, we are not looking billions of years back in a vague sense. We are looking to a few 100 million years after the Big Bang, when the first long-lived structures should still be learning how to exist. That era matters because it is supposed to be the beginning of structure, not the middle of it. It is the period when the first stars ignite and the first galaxies start to gather, turning pristine gas into the first engines of light. Before that ignition, the universe passes through a quieter interval, sometimes called the cosmic dark ages. The gas is mostly hydrogen and helium, cooling as it expands, and there are no stars yet to carve bright islands into the darkness. When the first stars finally form, they do more than shine. Their radiation begins to ionize the surrounding hydrogen, changing how matter interacts with light, and setting the conditions for everything that follows. The standard model of cosmology, called lambda CDM, gives a clear baseline for this unfolding. Dark energy drives late acceleration, and cold dark matter seeds early growth, providing gravitational wells that ordinary gas can fall into. This model did not appear overnight, and its confidence was earned through decades of converging evidence. Measurements of the cosmic microwave background, galaxy clustering, and primordial element abundances all point toward the same broad framework, even when the details remain contested. In that baseline, structure forms hierarchically, like a landscape built from small stones into larger walls. Small halos collapse first, then merge into larger systems over time, with gravity amplifying tiny initial fluctuations into the cosmic web. Those initial fluctuations are not guessed at randomly. They are measured as subtle temperature variations in the cosmic microwave background, ripples only tens of microkelvin deep, preserved from the universe's earliest transparent moment. The first galaxies in this picture should be modest and messy because they are still assembling their parts. They should be dominated by young stars, irregular shapes, and rapid bursts of formation, with turbulence and feedback constantly rearranging the gas. Their light should also carry the signature of youth. Massive, short-lived stars burn hot and blue, and their ultraviolet output should be intense, even if much of it is later absorbed by gas and dust. Chemical evolution should be gradual, because heavy elements must be manufactured and then dispersed. The earlier stars start with hydrogen and helium, then forge heavier elements in their cores, then spread them through winds and explosions that seed the next generation. Metals like oxygen should be rare at first, not because oxygen is exotic, but because it is earned. It requires generations of stars to build it and time to mix it into gas, so early spectra are expected to look chemically simple. Black holes should grow alongside their hosts, but not outrun them by too much, at least in the standard picture. In many nearby galaxies, the mass of the central black hole correlates with the galaxy's bulge, suggesting a long coevolution shaped by feeding and feedback. None of this says the early universe is empty, and Webb was never expected to find nothing. It says the early universe is young, and youth should show in its scale, its disorder, and its incomplete chemistry. Webb's first wave of results complicated that expectation, and the complication was not subtle. Several candidate galaxies appeared surprisingly massive for their redshifts, as if they had already completed a long period of growth before the universe reached its first 500 million years. Mass in astronomy is not measured directly, because we cannot put galaxies on a scale. It is inferred from light, colour, and models of stellar populations, which means every number carries assumptions about how stars form and how they age. Even with that caution, the implied numbers were provocative, and they landed like a challenge. Some objects looked like they had already built billions of solar masses in stars, implying a pace of assembly that strains the usual timelines. If those masses are real, the growth rate becomes extreme, and the universe must work efficiently. It demands either unusually efficient star formation or unusually early assembly, or both working together inside the densest dark matter halos. The tension is sharpened by a simple arithmetic of time. When only a few 100 million years are available, every episode of star formation must be intense, and every delay caused by feedback or heating becomes more consequential. Then came the black holes, which add a different kind of pressure to the story. Webb and other observatories pointed to early quasars and active nuclei that seemed overgrown, their brilliance implying accretion onto black holes already enormous by any ordinary standard. A quasar is not just a bright galaxy, and the distinction matters. Its light is powered by matter heating as it falls toward a black hole, converting gravitational energy into radiation with an efficiency that can outshine the combined starlight of the host. Some black holes appeared too heavy relative to their galaxies, at least compared with local scaling relations. The usual proportionalities looked strained at the earliest times, as if the black hole growth curve had accelerated ahead of the galaxy's own buildup. To make such black holes quickly, you need a head start, and the options are limited. You need massive seeds, or super Eddington feeding, or both, because ordinary steady accretion struggles to reach 1 billion solar masses so early. The Eddington limit is a kind of cosmic speed limit, set by the balance between gravity pulling in and radiation pushing out. Exceeding it is not impossible, but it requires special conditions, and those conditions must be common enough to explain what we see. Chemical hints added another layer because chemistry is a clock with its own tick rate. Reports of oxygen at very high redshift suggested rapid enrichment, perhaps faster than standard timelines assume, and therefore faster cycling of gas through stars. Oxygen is not just a detail, and it is not merely a line in a spectrum. It is a sign that stars lived, died, and recycled matter earlier than expected, implying that stellar populations may have matured quickly inside compact, efficient star-forming regions. If oxygen is present, then supernovae must have already occurred, and their shock waves must have mixed metals into surrounding gas. That mixing is not instantaneous, so the signal hints at both early star formation and early redistribution of enriched material. Beyond individual galaxies, there were claims about structure itself, which is where unease becomes almost architectural. A reported feature in the cosmic web seemed far larger than models predict so early, suggesting that the scaffolding of matter may have assembled faster than expected. Large-scale structure is the universe's scaffolding, a network of filaments and nodes shaped primarily by dark matter. It grows from tiny fluctuations measured in the cosmic microwave background, then evolves as gravity amplifies contrast over billions of years. If a web-like structure is too big too soon, it challenges the pace of growth in a direct way. It pushes on the link between early conditions and later clustering, because the same physics that shapes small halos also shapes the largest patterns. And hovering over all of this is a separate, older puzzle, one that predates Webb but now feels newly relevant. The Hubble tension is the mismatch between expansion rates measured in different ways, and it has resisted easy explanations. One method reads the early universe through the microwave background and a model, extracting a present-day expansion rate by fitting parameters. Another measures the late universe through distance ladders and supernovae, building a local calibration step by step. The two answers disagree beyond comfortable error bars, and the disagreement has persisted through improved data. If the expansion history is off, then the inferred ages and distances at high redshift can shift too, and the early universe's timetable may need recalibration. These are not isolated curiosities scattered across separate papers and separate instruments. Together they form a question about scale, speed, and timing in the first half-billion years, when the universe transitions from simplicity to complexity. How can structure appear so quickly in a universe that has barely begun, at least by our intuition of time? How can galaxies look mature when the cosmic clock reads only a few 100 million years, and when the raw ingredients should still be settling? The questions become sharper when we picture what Webb is actually seeing. Each bright speck in a deep field is a whole system, and each system is a fossil record of gas inflow, star formation, and feedback, compressed into a tiny patch of sky. Before we declare a crisis, we have to face the hardest part of astronomy. We do not touch these objects. We interpret them, and interpretation is where the universe can hide its tricks. Webb does not hand us masses and ages, and it never claims to. It gives spectra, colours and brightness. Then we translate those into physical stories, using models that are powerful but never perfectly unique. That translation can go wrong in ordinary ways, and ordinary errors can look like extraordinary discoveries. Dust can redden light and mimic older stellar populations, because dust preferentially absorbs blue photons and lets redder light pass. A dusty starburst can look like a massive evolved galaxy if the models are too simple. The same photons can support multiple histories, and the difference between them can hinge on how we model attenuation, geometry, and hidden star formation. Dust itself is not guaranteed to be scarce early on, and that uncertainty matters. It can form in supernova ejecta and in the winds of massive stars, and if it survives shocks, it can build up faster than our simplest timelines suggest. Gravitational lensing can also deceive, and the deception is built into relativity. A foreground mass can magnify a background galaxy, making it appear brighter and therefore more massive, while also distorting its shape in ways that can be subtle at low signal. Selection effects matter in deep surveys because we are not sampling the universe evenly. We detect what is easiest to detect, and the brightest early objects may not be typical, which can bias our first impressions of an entire epoch. Photometric redshifts can mislead, especially when the data are sparse or the templates are imperfect. When redshift is estimated from colours rather than precise spectral lines, a lower redshift interloper can masquerade as ancient, simply by mimicking a break in the spectrum. Even when redshifts are confirmed spectroscopically, interpretation remains, and the uncertainty shifts rather than vanishes. Converting light into stellar mass depends on assumptions about the initial mass function. The distribution of stellar masses formed in each burst. It depends on star formation history, because a brief, intense burst produces different colours than steady formation over time. It depends on how quickly dust forms and how it absorbs and re-emits energy, shifting starlight into infrared emission that may or may not be fully captured. It depends on feedback physics that we still tune in simulations because feedback is messy and multi-scale. Supernova winds, radiation pressure, and black hole jets can all change growth rates, either by expelling gas or by compressing it into new star-forming pockets. So the first tension is methodological, and it is a tension about inference. Are we seeing genuinely massive early galaxies, or are we overestimating mass from limited information, because our models are being asked to extrapolate beyond familiar territory? The second tension is physical, and it begins only after the first is addressed. If the measurements hold, then something in our story of early growth is missing, and the missing piece must operate quickly and widely. One possibility is that astrophysics is more efficient than we thought, especially under early conditions. Gas could cool faster, stars could form in denser bursts, and feedback could be weaker early on, allowing more of the available baryons to turn into stars. Black holes could start bigger, which changes the entire race. Direct collapse scenarios could plant seeds that leapfrog the slow path from stellar remnants, forming massive black holes from collapsing gas clouds before ordinary star formation fragments them. Dust could appear earlier through rapid production channels and then reshape what we infer from colours. Metal enrichment could proceed in intense cycles inside compact systems, where repeated bursts and explosions quickly raise the chemical baseline. Those changes would revise galaxy formation without rewriting cosmology, and that distinction is important. They would keep lambda CDM intact while adjusting the messy baryonic details, the part of the story where gas, radiation and turbulence complicate clean gravitational growth. But there is a more unsettling possibility, and it is the one that draws the most attention. The timeline itself might be strained, or the initial conditions might differ from what we infer, which would ripple outward into many other measurements. If the expansion history is different, then ages at a given redshift shift, and the early universe may have had more time than we think. If dark energy behaves differently, the growth of structure can change, altering how quickly halos collapse and merge. If dark matter is not perfectly cold, small-scale formation changes, because warmer particles erase small fluctuations. If there are early dark sector interactions, growth could accelerate or suppress in unexpected ways, changing the abundance of early halos that host the first galaxies. Even small departures can cascade, because early structure sets the stage for later milestones. Early structure sets the stage for reionization, for the first metals, and for the later galaxy population. so a shift at the beginning can echo through the entire cosmic narrative. That is why these early Webb results matter, beyond the thrill of new images. They're not just about a few galaxies, they're about the universe's ability to build complexity fast, and about whether our accounting of time and growth is internally consistent. The core mystery becomes a question of scale, stated in the simplest possible terms. How big can things get? How early, given the time available and the rules we think apply, and how confident are we in the rules we're using? This film does not begin by choosing a side, because certainty would be premature. It begins by treating the discomfort as data, and by asking what kind of error, or what kind of physics, could produce this particular pattern of surprise. If we are being fooled, we need to know exactly how, and the mechanisms are specific. If the universe is surprising us, we need to know exactly where the model bends, and whether it bends in astrophysics, in cosmology, or in both. Either way, the path forward is the same, and it begins with measurement rather than speculation. We need a reliable ruler for distance and a reliable clock for cosmic time, because without them every anomaly can be an illusion of scale. We need to know what redshift really tells us, and what it hides, because redshift is both a measurement and a model-dependent interpretation. We need to know how mass is inferred, and where the uncertainties live, because mass is the currency of structure formation. We need to understand how expansion is measured, and why different methods disagree, because the Hubble tension is not a side plot anymore. Only then can we judge what Webb is actually revealing, and whether the early universe is truly moving too fast. So we step back from the images and into the machinery behind them. We start with the cosmic ruler and the cosmic clock, because scale is the heart of the unease, and because every claim must ultimately be translated into time. We step back from Webb's images and into the machinery behind them, because the unease in Chapter 1 was about scale, and scale lives inside measurement. In the dark between galaxies there is no tape measure, no yardstick floating in space, only light arriving after a long and complicated trip. Webb shows us glittering points and smeared arcs, yet the real story begins earlier, when a photon leaves a source and starts keeping time. Astronomy begins with photons, not objects, because every distance, age, and mass is a translation from light into a physical story. We do not touch a galaxy to weigh it, and we cannot stand beside it to judge its size. Instead, we infer, we calibrate, and we compare, building a chain of reasoning that is elegant when it holds, and unsettling when it doesn't. The first translation is redshift, written as Z, and it is not simply a Doppler effect from motion through space. Doppler redshift is familiar from everyday life, like a siren changing pitch as it passes, and that intuition is useful at small scales. Cosmological redshift is stranger, because it is not caused by a galaxy racing through a static arena. It is caused by the arena itself changing while the photon is in flight. Cosmological redshift measures how much space itself has stretched during a photon's journey, so wavelength is pulled longer by expansion. A wavelength leaves one universe and arrives in a larger one, as if the grid beneath it slowly relaxed. In a simple picture, the photon's crests are like marks on a rubber sheet, and the sheet expands between departure and arrival. The photon does not lose identity, but it does lose energy, because longer wavelength means lower frequency. That distinction matters because expansion is not a background detail. It is the conveyor belt that turns distance into time, and it sets the tempo of cosmic history. When we say we are looking far away, we are also saying we are looking back. The farther the light travelled, the earlier the scene we're watching, and the stretching of space is the conversion factor. At low redshift, Doppler intuition works well enough for many purposes, because the universe has not changed dramatically over the photon's travel time. Nearby galaxies also carry peculiar velocities, local motions caused by gravity, and those can dominate the redshift at very small distances. In that regime, redshift is a messy blend of expansion and local motion, and astronomers correct for it with models of the local flow. At high redshift, the geometry and history of expansion dominate the interpretation, and peculiar velocities become a smaller fraction of the signal. Redshift becomes a ruler only after we choose cosmological parameters, because the mapping from Z to distance is not universal. Matter density, dark energy density, and curvature set the relationship between redshift and the size of the observable universe. Even the simple-looking Hubble law, where velocity scales with distance, is only a local approximation. Farther out, the curve bends, because the expansion rate has changed across time. Redshift becomes a clock only after we integrate an expansion history, which means we add up how fast the universe expanded at each epoch. Look-back time depends on H0 and on how the universe's contents dilute and evolve, because matter thins as volume grows while dark energy behaves differently. In plain terms, the universe has not expanded at one steady pace. It slowed when matter dominated, then later began accelerating as dark energy took over. So a measured z is a clean number, but its meaning is model dependent, and that dependence is not a technical footnote. The same redshift can imply slightly different ages under slightly different assumptions, and those differences accumulate at early times. When Webb pushes into redshifts where the universe is only a few 100 million years old, a shift of tens of millions of years can change what seems possible. How quickly can gas cool, collapse, and build stars, and how quickly can those stars assemble into a massive galaxy? Distance is the next translation, and distance is not one thing, because light propagates through an expanding space-time. Astronomers use several distance definitions, each designed to preserve a particular relationship that would be simple in a non-expanding universe. The vocabulary can feel abstract, but it is really a set of tools for not fooling ourselves. If we use the wrong distance for the wrong question, we can make the universe contradict itself. Co-moving distance tracks positions in the expanding grid, as if we freeze the expansion and label coordinates on the cosmic fabric. It is useful for large-scale structure, because it lets us compare where things are relative to the expanding background. Proper distance changes with time because the grid itself grows, so the separation between two co-moving points increases even if neither object moves. This is why galaxies can be at rest in co-moving coordinates while still receding from us. Luminosity distance connects flux to intrinsic power, and it bakes in expansion effects that dim light beyond simple inverse square spreading. Photons arrive with less energy because they are redshifted, and they arrive less frequently because the source's time is stretched in our frame. Those two effects multiply, so distant objects are dimmer than you would expect in a static cosmos. When we infer luminosity, we are silently applying this cosmological bookkeeping. Angular diameter distance connects physical size to observed angle, and it behaves counterintuitively at high redshift. In an expanding universe, there is a redshift where angular size reaches a minimum, after which even more distant objects can appear larger again. That reversal is not a trick of the telescope, it is geometry, a reminder that light paths and distance measures are warped by cosmic history. These are not competing choices, they are different projections of the same geometry, and each is correct in its own context. The danger is mixing them casually when building physical intuition, because our brains are trained on Euclidean space. A galaxy can be far in co-moving distance, faint in luminosity distance, and oddly sized in angular diameter distance, all at once. When Webb gives us a tiny smudge at z equals 10, we're not just seeing a far object. We're seeing a bundle of definitions that must be kept consistent. To anchor any of these distances, cosmology needs calibration, and that is why the distance ladder exists. It is a pragmatic invention, built over a century of astronomy, and it is both powerful and fragile. Each rung reaches farther than the previous one by using objects whose intrinsic properties can be standardized. If one rung is slightly warped, every rung above it leans. The first rung is parallax, the only geometric method that does not rely on astrophysical assumptions. Earth's orbit provides a baseline, and stars shift against background positions over the year. The angle is tiny, measured in arcseconds and fractions of arcseconds, and it shrinks with distance. In the visual language of the film, parallax is a slow, precise wobble, stars sliding back and forth against a deeper, almost motionless field. Parallax is simple in concept, but difficult in execution, because the measurement is fighting instrument behavior as much as it is fighting the sky. Systematics hide in instrument stability, detector geometry, and the statistics of crowded fields, where overlapping sources can pull centroids. The atmosphere once limited parallax from the ground, and space missions were designed to escape that blur. Yet even in space, thermal changes, scanning patterns, and subtle optical distortions can imprint biases. Gaia made parallax a revolution, mapping more than 1 billion stars with unprecedented precision, but it is not an absolute endpoint. Even tiny zero-point offsets matter when parallax calibrates everything above it, because the ladder amplifies small errors. A micro-arc-second mistake is a whisper in the data, yet it becomes a measurable shift in H0 when propagated through Cepheids and supernovae. The ladder rewards humility because the universe punishes overconfidence. The next rung is Cepheid variables, stars that pulse with a period tied to their luminosity, a relationship discovered in the early 20th century. Henrietta Leavitt found the period-luminosity relation by studying Cepheids in the Magellanic Clouds, where the stars were effectively at the same distance. That historical detail matters because it shows how astronomy often advances, by finding a pattern, then turning it into a tool. Measure the period, infer the absolute brightness, then infer distance by comparing to the observed brightness. Cepheids are bright enough to reach nearby galaxies and stable enough to serve as standards, which is why they became a cornerstone of modern cosmology. They are also messy enough to carry hidden biases, because real stars are not idealized points. Cepheids live in star-forming regions where dust and crowding are common, and their light curves can be affected by companions. In images, they are not isolated beacons, but flickering notes inside a noisy orchestra. Dust dims and reddens Cepheids, and extinction laws vary by environment, which means a correction that works in one galaxy may fail in another. If dust corrections are off, distances drift in a coherent direction, and coherent drift is the most dangerous kind. Metallicity changes Cepheid atmospheres and therefore their brightness at a given period, because metal content affects opacity and pulsation physics. If metallicity trends differ between calibrator galaxies and target galaxies, the ladder tilts without announcing it. Crowding blends light in distant hosts, making Cepheids appear brighter than they are, and that bias grows with distance. A blended Cepheid looks closer than it truly is, which can mimic a higher expansion rate when used to calibrate supernovae. Calibration drift can also enter through filters, detectors, and photometric pipelines, because different instruments do not see the sky in exactly the same way. A small mismatch between instruments can become a large mismatch in inferred distance, after the ladder has done its multiplying. The next rung is type Ia supernovae, thermonuclear explosions used as standardizable candles, and their role in cosmology is both dramatic and delicate. A white dwarf, pushed toward instability, ignites runaway fusion and briefly outshines its entire host galaxy. The peak brightness correlates with light curve shape and colour, so astronomers can correct for differences and reduce scatter. In visuals, a supernova is a sudden flare, an expanding shell of light that fades over weeks, leaving a fingerprint in the light curve. Supernovae extend the ladder deep into the Hubble flow, where peculiar velocities average out and expansion dominates. They turn local calibration into a cosmic measurement, because they can be seen across hundreds of megaparsecs. But supernovae also carry systematics that do not average away, and those systematics can masquerade as cosmology. Dust in host galaxies, intrinsic colour variations and population evolution can bias standardization, especially if the supernova population changes with redshift. Selection effects matter, because surveys find brighter events more easily, and that can skew the sample. Malmquist bias can make distant samples look systematically more luminous, which again pushes distances and H0. Even the definition of a clean sample can shift results, because different cuts on extinction, light curve quality, and host properties can move H0 by meaningful amounts. The ladder is not a single measurement, it is a chain of linked inferences, and each rung inherits the uncertainties of the rungs below. That is why calibration differences cascade, and why the cascade is so hard to stop once it begins. A 1% shift in Cepheid's 0 point does not stay 1% when propagated through supernova cosmology, because it changes the absolute scale of the entire Hubble diagram. This cascading is the quiet engine of cosmological crisis, because the target precision is now a few percent. At that precision, every small systematic becomes a potential headline, and every headline becomes a question about what we truly know. Standard candles are one strategy, but not the only one, and cosmology has learned to diversify its tools. The universe is not obligated to provide perfect light bulbs, so we also search for standard rulers, features with a known physical size. If candles translate brightness into distance, rulers translate patterns into distance. The most important ruler is baryon acoustic oscillations, or BAO, and it is a fossil imprint of sound waves in the early universe. Before atoms formed, the universe was a hot plasma of photons, electrons, and baryons, dense enough that light could not travel freely. Photons scattered constantly, and pressure-supported acoustic waves, like ripples in a fluid that refuses to settle. Overdense regions tried to collapse under gravity, but radiation pressure pushed back, setting up oscillations. Dark matter did not feel that pressure, so it began collapsing earlier, forming gravitational wells that baryons could not fully occupy yet. Baryons were dragged by radiation until recombination released the photons, and that release is one of the great transitions in cosmic history. When the plasma cooled enough for electrons to bind to nuclei, photons decoupled and streamed freely, creating the cosmic microwave background. The sound waves froze into a preferred separation scale, because the pressure support vanished and the wavefront stopped propagating. That scale is the sound horizon, set by early universe physics, and it becomes a standard ruler imprinted in the clustering of galaxies and intergalactic gas. Bao is measured as a slight excess in pair separations, a statistical ripple across large surveys, and it is subtle enough that no single galaxy reveals it. Instead, the signal emerges when we map millions of galaxies and measure how often pairs appear at different separations. In a visualization, it looks like a faint ring in a sea of points, a ghostly circle that only appears when the data are stacked and averaged. It is robust when the volume is large, because random galaxy formation details wash out, leaving the primordial imprint. Bao can be read in transverse direction as an angular scale, and it can be read along the line of sight as a redshift separation. Those two readings constrain different combinations of distances and expansion rates, which is why Bao is so valuable. Bao therefore maps the expansion history across cosmic time, giving us checkpoints between the nearby ladder and the ancient CMB. It is a ruler that works precisely because it is not about individual galaxies, but about the statistical skeleton of the cosmos. Bao is powerful because it is less sensitive to astrophysical details of individual galaxies, and that reduces one category of uncertainty. It relies on large-scale statistics, not on the quirks of stellar populations, dust lanes, or starburst episodes. But Bao still depends on early universe calibration, because the ruler's absolute length comes from physics before recombination. That ties Bao to the cosmic microwave background, whether we like it or not, because the CMB is where the sound horizon is measured most cleanly. The CMB is the boundary condition of modern cosmology, the oldest light we can see, and it arrives as a nearly uniform glow with tiny temperature variations. Those variations are not noise, they are the seeds of everything later. Its temperature pattern encodes the density of matter and baryons, the amplitude of primordial fluctuations, and the geometry of space. It also encodes the sound horizon scale, which appears as a characteristic angular size in the pattern of peaks. From the CMB alone, we do not directly measure today's expansion rate, because the CMB is a snapshot from long ago. We infer H0 by fitting a model, usually LCDM, and evolving that model forward through cosmic time. Under LCDM, the CMB yields a precise H0, because the parameter set is tightly constrained, and the physics is internally consistent. Change the model, and the inferred H0 can shift, because the same CMB pattern can be explained by different combinations of ingredients. This is the key philosophical divide in the film, and it is as much about inference as it is about data. Local methods measure distances and expansion directly in the late universe, while early methods infer today from the early universe. Both approaches are rigorous, but they are rigorous in different ways, and that difference matters when they disagree. One is a calibrated ladder built from nearby anchors, and the other is a model-based extrapolation from a boundary condition. The Hubble constant, H0, becomes the recurring heartbeat because it connects every chapter's stakes. It sets the present expansion rate and influences inferred ages and distances, including the time available for galaxies to form. In local measurements, H0 emerges from Cepheids calibrating supernovae, then fitting the slope of the distance, redshift relation. The result sits near the low redshift universe we can map in detail, where we can inspect hosts, dust, and environments. In early universe inference, H0 emerges from CMB fits combined with LCDM, and the result is a prediction for today. It is derived from the universe's first observable surface, then carried forward by equations that encode how matter and dark energy shape expansion. The tension is that these two answers disagree by a few kilometers per second per megaparsec, and that sounds small until you compare it to the quoted uncertainties. In a field that is now measuring at the percent level, a few units is a crack, not a rounding error, A few kms MPC changes the inferred size of the observable universe and the age of the cosmos by amounts that matter, especially when we are counting hundreds of millions of years. It also changes the time available for early structure to grow, which feeds directly into Webb's early galaxy surprise. If the local value is right, the universe expands faster today than LCDM predicts from the CMB, and something in the model or in early physics may be missing. If the CMB inferred value is right, then some part of the distance ladder may be biased, and the crisis is methodological, not fundamental. The film's central question sharpens here, because Webb's images are not just pretty. Are Webb's early massive galaxies a crack in the standard model, or a misreading of light and calibration? The question is not rhetorical, and it is not a simple choice between hero and villain. It is a demand that we examine every translation step, because each step can bend reality into an illusion. To answer that, we also need to understand how astronomers turn light into mass, because Webb's shock was not just redshift, it was implied stellar mass, numbers large enough to feel premature like skyscrapers rising before the concrete has set. Stellar mass is usually estimated through spectral energy distributions, or SEDI fitting, where we compare observed colours and spectra to libraries of stellar population models. The method is powerful because it uses all available wavelengths, and it is dangerous because different histories can paint similar colours. SED fitting is degenerate because age, dust, metallicity and star formation history can trade places in the models. A galaxy can look red because it is old, or because it is dusty, or because strong emission lines are boosting certain bands while suppressing others. The first major assumption is the initial mass function, the IF, which specifies how many low-mass and high-mass stars form in a population. Low-mass stars are faint but long-lived, and they store mass quietly for billions of years. A bottom-heavy IMF hides mass in faint stars, raising mass-to-light ratios, which makes a galaxy heavier than it looks. A top-heavy IMF produces more light per unit mass, lowering inferred stellar mass, and it can also change chemical enrichment and feedback. Most analyses assume an IMF similar to the Milky Way, because it works nearby and because it is a convenient default. The early universe may not share that assumption, and Webb forces the question with every unexpectedly bright compact source. The next assumption is star formation history, and this is where time becomes a modelling choice. A single burst, rising formation, or continuous formation changes the mix of stellar ages and therefore the colours. Young populations are dominated by massive blue stars, while older populations fade and redden as short-lived stars die. Age and dust can mimic each other in broadband photometry, so a dusty young galaxy can resemble an older, more massive population if the models are too restricted. Dust attenuation is not a single number. It is a curve with wavelength dependence, and different dust geometries change what we observe. Dust can sit in a foreground screen, or it can be mixed with stars, or it can clump into opaque knots that hide star formation completely. Grain properties matter too, because small grains and large grains absorb and scatter differently, reshaping the spectrum. When we correct for dust, we are not just brightening the galaxy, we are choosing a physical story about where the dust sits and what it is made of. Metallicity also reshapes spectra by altering stellar atmospheres and nebular emission, and it evolves as stars forge heavier elements. Early galaxies may have low metallicity, but rapid enrichment can complicate that expectation, especially in intense starbursts. Nebular emission lines can contaminate broadband filters, boosting flux in specific bands, and at high redshift those lines slide through infrared filters like moving targets. If not modelled correctly, line emission can inflate inferred stellar masses by making a galaxy seem to have more continuum light than it does. Webb's infrared sensitivity makes these issues unavoidable, because it captures rest frame optical light at high redshift where both continuum breaks and emission lines matter. The data are richer than before, yet the interpretation can be more delicate because the models must keep up. A sharp spectral break might indicate an older population, but it might also be shaped by dust or by a forest of lines. The telescope gives us more truth, and it also gives us more ways to be subtly wrong. Gas mass is estimated differently, often through emission lines from cold gas tracers, because gas is the raw material for future stars. In the local universe, CO lines and dust continuum are common proxies, and they are calibrated against well-studied galaxies. At high redshift, observers may use C2 or other far-infrared lines, or infer gas from star formation rates and depletion times. Each method carries conversion factors that may evolve, and evolution is exactly what the early universe specializes in. Those conversion factors depend on metallicity and radiation fields, which change the chemistry and cooling of the interstellar medium. A low metallicity galaxy can be gas-rich but line-faint, which can hide mass in plain sight. If we underestimate gas, we may misunderstand how quickly a galaxy can keep forming stars. If we overestimate gas, we may imagine a reservoir that's not really there, and both errors feed into the same narrative about rapid assembly. Dynamical mass is the closest thing to weighing a galaxy, because it relies on gravity rather than on light. If we can measure rotation or velocity dispersion at a size scale, then the motions reveal the mass required to hold the system together. But dynamical mass is hard at extreme redshift because spatial resolution is limited and galaxies can be turbulent. Inclination uncertainties, non-circular motions, mergers, and feedback-driven outflows can blur the inference, and a young galaxy may not be in equilibrium at all. When dynamics are available, they can test SED-based stellar masses, and that test can be decisive. A stellar mass larger than the dynamical mass is a red flag, because stars cannot outweigh the gravity that contains them. That mismatch can point to modelling errors, lensing magnification, or misidentified redshifts, and each possibility has different implications. The point is not that said fitting is unreliable. The point is that it is conditional, and conditions matter most when the claims are extraordinary. All of these mass estimates depend on distance, because luminosity scales with distance squared, and luminosity feeds directly into inferred mass. A small distance error changes luminosity, and a luminosity change shifts mass-to-light inferences even if the stellar population model is perfect. So distance and mass are coupled uncertainties, not separate ones, and Webb's early universe claims sit exactly at that intersection. When we argue about early massive galaxies, we're often arguing about the ruler without saying so. Then there is gravitational lensing, the universe's own optical trick, predicted by general relativity and confirmed across a century of observations. Foreground mass bends light and changes what we think we see, because space-time curvature redirects photon paths. Lensing can magnify a background galaxy, making it appear brighter, and therefore more massive if we do not correct for it. It can also stretch and multiply images, turning a single galaxy into several mirrored fragments. Strong lensing is obvious when arcs and multiple images appear, and the visuals are unmistakable, curved streaks around a massive cluster, like light poured into a whirlpool. Weak lensing is subtle and can still bias samples by preferentially boosting detectable sources, especially near the detection threshold. Lensing helps because it reveals fainter galaxies than Webb could otherwise see, effectively lending the telescope extra power. It misleads because magnification bias can make rare bright objects seem more common than they truly are. If early massive galaxies are preferentially lensed, the inferred abundance is inflated, and abundance is the real cosmological pressure point. If lens models are uncertain, the inferred intrinsic luminosities are uncertain, and that uncertainty propagates into mass. Even without lensing, selection effects shape what Webb finds first, because deep surveys are biased toward the brightest, highest surface brightness objects at a given redshift. The first detected population may not represent the typical building blocks of later galaxies, and that is a quiet trap in every frontier survey. So the measurement foundation has two tasks, and both are essential to the film's mystery. It must explain how we infer distances and masses, and it must explain how errors masquerade as new physics. This is where the documentary's tone turns deliberately cautious, because caution is not pessimism. It is respect for the complexity of inference, and for the fact that the universe does not label its variables. Before we declare a crisis, we have to locate where the ruler can bend. The ruler can bend in calibration, through parallax zero points and photometric cross-instrument offsets. The ruler can bend in astrophysics, through dust, metallicity, and stellar population assumptions that are reasonable nearby but uncertain early. The ruler can bend in cosmology, through the mapping from redshift to time and distance, which depends on parameters we're still refining. The ruler can bend in statistics through selection and lensing bias, which can sculpt the sample before we ever interpret it. Yet the tension remains because the methods are independent in important ways, and that independence is what makes the disagreement so provocative. Cepheids and supernovae live in the late universe, where we can cross-check environments and systematics. The CMB lives at recombination, where the physics is linear, clean, and encoded in a pattern that has been measured with exquisite precision. BO bridges the middle and often agrees with the CMB under LCDM, which tightens the net around the local ladder and also tightens the net around the model. So the Hubble tension is not a single disagreement. It is a network of constraints that do not all meet at one point, like rulers laid end to end that refuse to align. If we adjust the ladder, we must explain why multiple cross-checks did not catch the bias. If we adjust the model, we must preserve the CMB's detailed success, including the pattern of peaks that has become cosmology's proudest achievement. That is why a few KLMS MPC matters, because it is not the number itself. It is what the number implies about hidden systematics or missing physics. The tension also feeds back into Webb's early universe, because expansion history controls the time available at a given redshift. More time makes early massive galaxies less shocking, because there is more room for star formation, mergers, and growth. Less time makes them more shocking, forcing higher star formation efficiencies and faster assembly in a universe that is still young. When we watch Webb's deep fields, we are watching a race against the clock, and H0 is part of the clock's gearing. So Webb's headline results cannot be separated from the cosmic ruler, because the ruler is the story's infrastructure, and H0 is the stress test. We now have the measurement vocabulary needed to interpret the next claims, even if the vocabulary feels like a warning label. Redshift is stretch, distance is model-linked, mass is inferred, and lensing can distort. The next step is to return to Webb's deep fields with this framework in hand, and ask whether the early universe is truly overgrown, or whether our conversions are. Now that we know how mass and distance are inferred, we can examine Webb's headline shock. Galaxies that appear too massive to exist so early demand either new physics or better accounting, and the difference between those options is the difference between a revised model and a revised measurement. On screen, the deep field is a velvet black ocean punctured by pinpricks of light. Webb's infrared vision turns faint smudges into coloured beads and then into thumbnails with edges, cores, and hints of spiral-like asymmetry. When you label those beads with redshift estimates, the labels read like a dare, 10, 12, even higher. The camera lingers on a few bright knots, and you can almost feel the temptation to call them finished. The alarm was not about one object, but about a pattern across early catalogues, repeated in multiple reductions and multiple teams. At redshifts above 10, brightness implies either extreme star formation or extreme mass, because distance and cosmic dimming are relentless. The inverse square law punishes flux, and cosmic expansion adds an extra tax by stretching photons and slowing their arrival. If the redshifts are right, some systems seem to carry billions of solar masses in stars, not just gas. If the masses are right, they assembled in a few 100 million years, while the universe was still learning how to cool. This tension lands directly on the film's central question. Are Webb's early universe discoveries real cracks in the standard model of cosmology, or are they telling us we've been misreading the oldest light? It is a question about interpretation, as much as it is about existence. Because Webb does not hand us masses directly, it hands us photons, and then it dares us to translate them into history. Start with what Webb actually measured, because the chain matters. Webb measured fluxes through filters, and in some cases spectra with identifiable features, turning photons into numbers with error bars. Those error bars are not decoration. They encode background subtraction, detector noise, and the fact that some sources sit near the threshold of visibility. From those measurements, teams estimated redshift, then inferred luminosity, then modelled stellar populations, and finally translated light into mass. Each step is defensible, yet each step can shift as data improves, and small shifts compound into large conclusions. Historically, this is a familiar rhythm in astronomy, and it has a particular emotional signature. Hubble's first deep fields in the 1990s also produced galaxies that looked unexpectedly mature, and later work reclassified many of them. Even earlier, the first quasar redshifts felt like a shock, because the universe suddenly seemed capable of early extremes. The lesson was not that deep imaging lies, but that deep imaging tempts us to overinterpret sparse information. Early claims leaned heavily on photometric redshifts, because spectroscopy is expensive and faint targets are hard. Photometric redshift uses colours across bands to locate a sharp drop in flux, and it works best when the spectral energy distribution is sampled densely. That drop is often the Lyman break, where neutral hydrogen absorbs ultraviolet photons shortward of the 10^16 angstroms. In practice, the method is a pattern match between observed colours and libraries of possible galaxies. In plain terms, hydrogen in and around galaxies acts like a fog for ultraviolet light. At very high redshift, that ultraviolet light is stretched into the near-infrared, so the fog's signature moves into Webb's filters. The result is a striking pattern. One set of filters sees almost nothing, and then a redder set suddenly detects the source. It looks like a cliff edge in the data, and cliffs are persuasive. A high redshift galaxy should vanish in bluer bands, then reappear in redder infrared bands. That pattern can be convincing, and it can also be mimicked by lower redshift galaxies whose spectra have different breaks. Dusty or old populations can create a different break that looks similar in sparse data, especially when only a few filters bracket the drop. When templates are incomplete, the algorithm can choose the wrong era, and it can do so with high apparent confidence. The danger is not randomness, but systematic resemblance. The most common imposter is a lower redshift galaxy with a strong Balmer or 4000 angstrom break. That break comes from stellar atmospheres and metal absorption lines in older populations, and it can produce a sharp colour change. It is also tied to the accumulated history of star formation, because older stars dominate the optical continuum. If the photometry is noisy, the Balmer break can masquerade as the Lyman break, and the galaxy is suddenly promoted to the dawn of time. Spectroscopic redshift is stricter, because it looks for specific lines or breaks at precise wavelengths. A detected emission line can anchor the redshift, but line identification can still be ambiguous when the spectrum is noisy or the wavelength coverage is limited. One line can be mistaken for another if the continuum is faint, and the line is the only obvious feature. Multiple lines or a clear continuum break are the real lock, because they force the spectrum to agree with itself. In other words, the galaxy must tell the same story in more than one place. Webb's instruments change the playing field here. NIRSpec can disperse the light and reveal line forests, while NIRCam's Grism mode can provide lower resolution spectra over wide areas. MIRI extends reach to longer wavelengths, where rest frame optical light from early galaxies can land. Even then, the earliest targets are so faint that every photon feels negotiated, and integration times become a scientific choice. The telescope can see far, but time is still the currency. So the first reality check is simple, and it is also humbling. Some early candidates moved to lower redshift once spectra arrived, and the impossible label quietly fell away. Their brightness stayed the same, yet their implied distance and age changed, and the crisis eased because the clock lengthened. A few objects that looked like cosmic infants became merely distant adolescents. But not all candidates deflated, and that is where the chapter's unease lives. A subset remained at very high redshift even after better data and more careful modelling. Those objects became the core of the debate because they kept the same unsettling arithmetic, like a ledger that refuses to balance. The more you sharpen the pencil, the more stubborn the totals appear. To understand why the arithmetic feels unsettling, we need the baseline expectation. In LCDM, structure begins as tiny density fluctuations measured in the cosmic microwave background, at the level of 1 part in 100,000. Those fluctuations grow under gravity, and the growth is slow at first because the early universe is hot and radiation dominated. After recombination, when electrons and protons form neutral hydrogen, matter can clump more effectively, and the cosmic web begins to take shape. The universe moves from smoothness to scaffolding, and then from scaffolding to cities. Cold dark matter collapses first, because it does not feel radiation pressure and does not collide like gas. It forms halos that merge hierarchically, building larger halos over time through accretion and mergers. In simulations, those halos appear as knots in filaments, with smaller knots streaming inward like beads on threads. The picture is elegant, yet it is also statistical, and statistics can feel personal when an outlier appears. Baryons follow the dark matter, but they are not free to collapse instantly. Gas must cool, lose pressure support, and settle into the halo potential, and cooling is a microphysical process with macroscopic consequences. Cooling depends on density, composition, and radiation backgrounds, and in the earliest halos the gas is nearly pristine. Without heavy elements, cooling relies on hydrogen and helium lines, and on molecular hydrogen that is easily destroyed by ultraviolet radiation. Even a small ultraviolet background can change the outcome by erasing the main coolant. This is why the first light problem has always been delicate. The earliest star formation is a race between gravity pulling gas inward and radiation heating it back up. Even when gas falls in, it can shock, heat, and stall, and the halo must be deep enough to hold it. There is a threshold in virial temperature, and crossing it changes what the gas can do. Below that threshold, collapse is hesitant, and above it, collapse becomes plausible. When stars finally ignite, they do not simply add light, they add regulation. They add feedback that can throttle growth, especially in small halos where escape velocities are low. Radiation heats gas and drives winds, supernovae inject energy and momentum, and both can expel fuel, turning a potential galaxy into a brief flare. The standard picture expects early galaxies to be bursty and fragile, with star formation rising and falling like a signal in noise. In that expectation, brightness is intermittent, not sustained. That is why very massive galaxies at Z greater than 10 should be rare. The halo mass function falls steeply at the high mass end, especially at early times, because there has been little time for mergers and accretion. To host a huge stellar mass, you need a huge halo, and huge halos should be scarce at those epochs. Abundance is the pressure point, because one extreme object can exist, but many extremes imply a changed distribution. The question becomes, are we seeing a few statistical miracles or a systematic shift? Webb's early samples seem to show more bright candidates than expected, and the word too many carried more weight than too bright. The immediate temptation was to translate brightness into stellar mass and declare a mismatch, because mass is what cosmology predicts most directly. Yet mass from light is exactly where the universe can hide its tricks, because light is produced by the most luminous stars, not by the most massive inventory. A small fraction of young stars can dominate the entire budget of photons. Stellar mass estimates usually come from SED fitting, which matches observed colours to model populations. The fit tries to infer age, dust, metallicity, and star formation history from limited data, and it must also assume an initial mass function. Those parameters are degenerate, especially when the spectrum is sampled by broad filters rather than detailed lines. A red slope can mean dust, or age, or both, and the difference can be billions of solar masses. The fitting process is a negotiation between plausible stories. Age, dust, metallicity degeneracy is not a technical nuisance, it is a structural ambiguity. A young, dusty galaxy can mimic an older, cleaner galaxy in broadband photometry, because dust removes blue light and leaves a red continuum. If the model prefers an older solution, it raises the mass-to-light ratio, because older populations contain many faint low-mass stars. That single choice can inflate stellar mass without changing observed flux, and it can make a newborn system look like a veteran. The galaxy does not change, our interpretation does, and here is where it gets unsettling. This single interpretive choice, made quietly inside a fitting algorithm, is the same choice that, a few years ago, produced headlines about galaxies so massive, so early, that they seemed to break cosmology itself. Some were called impossible. Some threatened to topple the standard model of the universe. But what if those monsters were never that big at all? What if the universe wasn't broken, only our reading of the light was? Keep watching, because the answer hides in a few overlooked details most analyses got wrong. The degeneracy is especially sharp in the early universe because we expect low metallicity, yet we do not know the true enrichment history. Metallicity changes stellar atmospheres and therefore colours, and it also changes the cooling of gas and the production of dust. It influences the strength of absorption features, and it changes how efficiently stars produce ionizing photons. When metallicity is uncertain, the fit has more room to wander, and the mass estimate inherits that uncertainty. In a sense, the earliest galaxies are punished for being unfamiliar. Nebular emission lines add another trap, and they are a trap Webb is uniquely sensitive to. In star-forming galaxies, gas around young stars emits strong lines like He-alpha, H-beta, and O-Threes, powered by ultraviolet photons from massive stars. At high redshift, those lines shift into Webb's infrared filters, landing right where we measure the continuum. A line can boost a broadband measurement and masquerade as extra continuum, like a spotlight mistaken for daylight. The effect is most dramatic when the equivalent widths are extreme, as they can be in young systems. If line contamination is not modelled, the SEDI fit can infer a stronger stellar continuum, because it assumes the extra flux is starlight. That pushes the model toward higher mass and sometimes toward older ages, because the colours appear smoother and redder than they truly are. The galaxy looks mature because the photometry is being brightened by gas, not by long-lived stars. It is a reminder that galaxies are not just stars, they are glowing plasma too. This is not a subtle effect in extreme cases. A single strong line can contribute a large fraction of the flux in a wide filter, especially when the continuum is faint. In that regime, the difference between massive galaxy and line-dominated starburst can be one modelling decision. It is a thin line between a crisis and a calibration. Assumed star formation histories also matter, because they encode an expectation about how galaxies grow. Many fits use simplified histories, like constant formation or a single burst, because the data do not demand more complexity. Real early galaxies may rise rapidly, then pause, then flare again as gas streams in along filaments. If the true history is rising, a constant model can misread the colours and overestimate mass, because it spreads star formation over too long a time. The model smears a sprint into a marathon. There is also a timescale issue hidden inside the fits. At z greater than 10, the universe is only a few 100 million years old. So old means something like 100 million years, not 10 billion. Yet even that fraction matters, because a population that is 100 million years old has a much higher mass-to-light ratio than a population that is 10 million years old. In early epochs, tens of millions of years are not details, they are eras. So the first set of escape hatches is methodological, and it is not a retreat from science. Better spectra, better line modelling, and more flexible histories can shrink the inferred masses, sometimes dramatically. This is why early headlines often soften, not because the data were wrong, but because the translation improved and the priors became less naive. The telescope stays the same, while the interpretation becomes more disciplined. Yet there is a second set of escape hatches that is physical, not procedural. Even if the redshifts hold, early galaxies could be brighter per unit mass than we assume, because their stellar populations could differ from nearby ones. That possibility leads directly to the initial mass function, a deceptively simple phrase for a profound uncertainty. It is one of the few knobs that changes light without changing distance. The IMF specifies how many low-mass and high-mass stars form in a population. A Milky Way-like IMF creates many faint low-mass stars that store mass quietly for billions of years, acting like a hidden bank account. A top-heavy IMF creates more massive stars that shine intensely and die quickly, returning much of their mass to the interstellar medium. For the same stellar mass formed, a top-heavy IMF produces more light, especially in the ultraviolet. It also changes the ratio of ionizing photons to stellar mass, which matters for reionization. In the early universe, there are reasons to suspect the IMF could shift. Low metallicity changes how gas cools and fragmentation controls the typical stellar mass. If gas cannot cool to very low temperatures, it forms fewer small clumps, and the stars that form may be more massive on average. This is often discussed in the context of population 3 stars, the first generation of metal-free stars, which may have been exceptionally massive and short-lived. Even a partial shift toward higher masses would brighten a young galaxy disproportionately. If the earlier star formation was more top-heavy, Webb would see bright galaxies with less underlying mass. The observed flux stays fixed, yet the inferred stellar mass drops, and the too big part of the story becomes less severe. The same adjustment also changes metal production and feedback, which then loops back into formation efficiency. More massive stars produce more ionizing photons and more supernova energy, which could either accelerate enrichment or blow gas out faster. The lever relieves one tension while tightening another. The IMF is hard to measure directly at high redshift, so it becomes a controlled uncertainty rather than a free parameter. It is an astrophysical lever that can relieve tension without rewriting cosmology, but it is not a lever you can pull indefinitely. If the IMF changes, it must change in a way that does not break everything else, including the observed chemical abundances and the evolution of galaxies at later times. The universe must remain self-consistent across billions of years. Dust is another lever, and it carries a paradox that feels almost literary. We expect the earliest universe to be metal-poor, and dust requires metals, because dust grains are built from elements like carbon, silicon, and oxygen. Yet some early candidates appear red, and redness can be interpreted as dust attenuation rather than age. If dust exists early, it implies rapid enrichment and rapid dust production, likely from supernovae and massive stars. It suggests that the first stellar deaths happened quickly and efficiently. dust reddening can mimic older stellar populations because it suppresses blue light and reshapes the continuum. A dusty starburst can look like a quiescent evolved system in limited photometry, particularly when the rest frame ultraviolet is heavily attenuated. That misreading inflates ages and masses, and it can also hide ongoing star formation behind a veil. The galaxy looks mature because its youth is obscured, and the fit mistakes absence of blue light for absence of young stars. The question becomes, is the red colour a sunset or simply smoke? There is also a geometry problem inside the word dust. Dust can be mixed with stars, or it can sit in clumps, or it can form a screen, and each arrangement changes the observed colours. In nearby galaxies, we can map dust lanes directly, but in the early universe we inferred dust from integrated light. That inference is powerful, yet it is also a reminder that we are compressing complex structure into a single curve. A single number for extinction can hide a galaxy's internal weather. Webb helps here, because it reaches into the mid-infrared where dust effects and rest frame optical features can be separated. Mid-infrared photometry can constrain the slope and locate breaks more reliably, and it can sample wavelengths less sensitive to dust attenuation. It can also reveal whether a red colour is a true continuum shape or a line-driven artifact. Even so, dust composition and grain size remain uncertain, especially in unfamiliar early environments where the first supernovae may dominate dust production. The grains themselves may be younger than the galaxies we're trying to weigh. Then there is lensing, the universe's quiet amplifier, and it operates whether we ask for it or not. A foreground mass can magnify a background galaxy, making it appear brighter and therefore more massive if we do not correct for it. In cluster fields, strong lensing is expected and often modelled, producing arcs and multiple images that announce the effect. In blank fields, weak lensing still exists and can bias samples near detection limits, subtly nudging some sources above the threshold. The sky is not a neutral window, it is a lensing landscape. Magnification bias preferentially selects the brightest apparent objects, which is exactly what early searches focus on. A slightly magnified galaxy is more likely to enter a high redshift candidate list, because it is easier to detect and its colours are measured with higher signal to noise. That can make rare, luminous systems seem more common than they truly are, and abundance estimates drift upward. Abundance is where LCDM feels pressure, so even modest lensing bias matters. The sample becomes a hall of mirrors, just subtle enough to miss. Correcting for lensing requires lens models and statistical care, and the difficulty depends on the field. In strong lensing, uncertainties in the mass distribution translate into uncertainties in intrinsic luminosity, and small changes in the model can change magnification significantly near critical curves. In weak lensing, the correction is statistical and depends on large samples and accurate knowledge of foreground structure. Early Webb results were based on small areas, which makes cosmic variance and selection bias more dangerous, because one patch of sky can be atypical. The first fields were breathtaking, but they were not yet representative. Cosmic variance is an old adversary with a new costume. The early universe is clumpy, and rare peaks are not evenly distributed across the sky. If Webb's first deep fields happened to land on an overdense region, the early catalogues would look unusually rich, and the anomaly would be partly geographic. The only cure is breadth. More fields, more area, more independent lines of sight. In cosmology, repetition is not redundancy, it is proof. So the debate became a sorting problem, and sorting is rarely glamorous. Which candidates are genuinely extreme, and which are extreme because of inference, which are high redshift and which are interlopers, which are massive and which are simply efficient at producing light, perhaps because of a young stellar population or strong emission lines. The work is patient, and it is the price of claiming a revolution. As spectroscopy expanded, some of the most dramatic claims softened, and the community's tone shifted from alarm to calibration. A few bright sources turned out to sit at lower redshift, and their implied masses became ordinary by cosmic standards. Others kept high redshifts but showed line emission that reduced inferred stellar masses, because the broadband flex was not pure starlight. The crisis became less about impossibility and more about uncertainty, and uncertainty is a legitimate scientific state. It is also the state in which discovery often lives. Still, a residue remained, and that residue matters because it persists across analyses. Even after revisions, Webb continues to find luminous galaxies very early, and some remain difficult to reconcile with conservative assumptions. Some show compact morphologies that appear surprisingly settled, with central concentrations and smooth light profiles. Morphology is not mass, yet it hints at rapid assembly and rapid dynamical evolution, because ordered structure usually takes time. Even a small disk-like elongation can imply angular momentum that has already been organized. On screen, these objects are tiny, but they are not featureless. They look like bright knots with faint halos, or like slightly elongated droplets, suggesting rotation or merging components. In earlier telescopes, they would have been single pixels, but Webb gives them shape, and shape invites interpretation. The viewer watches the image sharpen, and the mind fills in a story. If these objects remain both early and abundant, then astrophysics must work harder than expected. One option is faster baryon-to-star conversion in the densest early halos, where gas inflow is continuous and densities are high. Gas could cool efficiently in those regions, and star formation could proceed with fewer losses, especially if the gas is shielded from ionizing backgrounds. Feedback might be less effective if inflow is relentless, and potential wells are deep, because expelled gas is quickly replaced. The galaxy becomes a furnace that never runs out of fuel. Another option is earlier than expected halo growth within LCDM's allowed scatter. Rare peaks in the initial density field collapse first and grow quickly, and they are the seeds of the first massive structures. Those peaks are expected, but their abundance is tightly predicted by the statistics of the initial fluctuations. If Webb is sampling more of them than expected, then either statistics misled us, or the initial conditions differ in subtle ways. How many rare peaks can exist before rarity loses meaning? A third option is altered feedback efficiency, which sounds small but can be decisive. If early supernova winds couple less effectively to dense gas, more fuel stays bound and can form additional stars. If radiation escapes differently in low metallicity environments, heating could be reduced, and gas could remain cold enough to keep collapsing. Small changes in coupling can produce large changes in stellar mass at fixed halo mass, because the system sits near a threshold between retention and blowout. In that threshold regime, nature can flip outcomes with minor adjustments. There is also the possibility that what looks like one galaxy is a tight group, unresolved or barely resolved, whose combined light is being modelled as a single massive system. In the early universe, mergers are common, and close pairs are expected. If multiple components blend in photometry, the inferred mass and luminosity of the galaxy rise, while the true masses are distributed among smaller units. The deep field can hide crowds inside single points of light. If the anomaly persists beyond astrophysical tuning, then the conversation shifts toward new physics, and it does so reluctantly. The simplest route is a change in small-scale power, which controls how many early halos form at a given time. If primordial fluctuations had more power on small scales, more halos collapse early, and the early universe becomes more crowded with potential galaxy hosts. That could raise the number of early massive galaxies without changing late-time large-scale structure too much, although such changes are constrained by the CMB and by galaxy clustering. Any tweak must respect the universe's oldest photograph. Other routes involve the dark sector, where the rules are still partly unknown. Dark matter that is not perfectly cold can suppress small halos, which usually worsens the problem rather than solves it, because it delays structure formation. But dark matter interactions, early dark energy, or modified initial conditions could change growth rates in more nuanced ways. Each proposal must preserve the CMB's success while altering early structure enough to matter, and that balance is difficult. The standard model is not fragile, but it is tightly interlocked. This is where the documentary's tension becomes architectural. Galaxies are the visible tip of a dark matter iceberg, and Webb is measuring the tip with unprecedented clarity. If the tip is too big, the unseen foundation must be larger, denser, or assembled earlier than we thought. The question becomes less about any single galaxy, and more about the scaffolding that holds all galaxies up. The deep field becomes a stress test for the invisible. The key is that brightness alone is not the anomaly, because brightness can be produced by youth, by lines, by lensing, or by an IMF shift. The anomaly is brightness combined with inferred mass, inferred abundance, and inferred time available, all at once. Each inference depends on models, and models improve, yet the questions stay sharp. How quickly can the universe turn gas into stars, And how quickly can those stars gather into coherent systems? At what point does fast become too fast for the rules we trust? There is a philosophical edge here that astronomy often hides behind equations. We are trying to reconstruct a three-dimensional evolving universe from a two-dimensional image and a handful of colours. We are asking whether a faint red dot is a massive galaxy, a dusty starburst, or a cleverly magnified interloper, and the answer changes the story of cosmic beginnings. What else, we wonder, have we mistaken for certainty simply because it looked clean on a plot? So we hold two ideas at once, because the data demand it, and the uncertainties are real. The early universe may be less mature than the first headlines claimed, because some candidates were misclassified, and some masses were inflated. The early universe may still be more efficient than our baseline simulations assumed, because even conservative analyses leave very luminous systems at very early times. The mystery survives the corrections, which is why it remains worth filming. Webb is not delivering a verdict, it is forcing a recalibration of confidence. Some alarms were false positives caused by photometric ambiguity and modelling shortcuts, and that is a normal stage in exploratory science. Some alarms were early warnings that our prescriptions for star formation and feedback are incomplete, especially under primordial conditions. The dataset is evolving, and the meaning evolves with it, because interpretation is part of the measurement. In astronomy, the map and the territory are updated together. The central question remains, now with sharper edges and fewer easy exits. Are we seeing real cracks in LCDM's growth story, or are we learning that early starlight is easier to misread than we admitted? Either answer keeps the mystery intact, because both imply hidden complexity that Webb is only beginning to expose. The deep field is not just far away, it is unfamiliar. If it is astrophysics, then the first galaxies were stranger and more efficient than our nearby analogies, and the early universe was a laboratory for extreme star formation. If it is cosmology, then the scaffolding beneath galaxies is different, and the whole timeline shifts, affecting everything that forms afterward. In both cases, the deep fields stop being postcards and become interrogations. They ask how much we truly understand about beginnings. And there is a final reason this chapter cannot end with comfort, even if many headlines have cooled. Galaxies are only one kind of overachiever in Webb's early universe, and they are not the most dramatic. The next chapter turns to objects that do not merely shine early, they dominate early, and they reshape their surroundings. On screen, the scale shifts from spiral arms to a pinprick nucleus, then the pinprick becomes the story. A galaxy that looks like a faint smudge is suddenly framed by a bright core, and that core behaves like a furnace. In deep fields, the light is ancient and stretched red, yet the implication is immediate. Something compact is already enormous. In the nearby universe, supermassive black holes follow a rule of thumb. Their masses correlate with bulge mass and with stellar velocity dispersion. Astronomers learned this gradually, as dynamical measurements improved and the census of black holes grew beyond a few famous cases. The pattern emerged from many galaxies, not from one dramatic outlier, which is why it carries so much weight. The M-sigma relation is tight enough to feel like coevolution written into gravity. Typical black hole-to-bulge mass ratios are small, often around 0.1%. Put plainly, the black hole is usually a tiny fraction of the stars, even though it dominates the central gravitational potential. That contrast is part of the mystery. How can something so small in mass matter so much in influence? The correlation itself links very different scales. Velocity dispersion measures how fast stars orbit within the bulge, which reflects the depth of the galaxy's central potential well. Black hole mass, by contrast, is inferred from motions in the innermost parsec or even smaller. Yet across many systems, the numbers track each other as if the galaxy and its black hole kept a shared ledger over cosmic time. That local relationship is not perfect, yet it is stable across many galaxy types. It suggests galaxies and their central black holes grew together, trading fuel and feedback. The common story is a loop. Gas falls inward, stars form, the black hole feeds, and energy returns to the galaxy. Over billions of years, that loop can tighten into a relation that looks almost inevitable. Historically, this was not always the expectation. For much of the 20th century, quasars were discovered before their engines were understood, and the idea of billion solar mass black holes sounded extravagant. Only after decades of spectroscopy, radio imaging and theoretical work did the black hole interpretation become the standard. When the local correlations arrived in the late 1990s and early 2000s, they felt like a unifying clue, an empirical bridge between quasars and ordinary galaxies. Webb-era reports disturbed that comfort by shifting the scene to high redshift. Quasars and AGN appear when the universe is still young, yet their engines look enormous. Visually, the contrast is stark. A bright point source sits inside a barely resolved host, and the host sometimes looks like an afterthought. If the measurements hold, the black hole is not merely keeping pace with the galaxy, it is leading the race. Some early systems imply black holes of tens of millions to billions of solar masses. In several cases, the host galaxies look too faint to match those black holes. The faintness matters because stellar mass is usually inferred from starlight, and at high redshift that light is both dimmed and shifted into infrared bands. Even with Webb sensitivity, the host can be a whisper under the quasar's shout. The startling claim is not just that early black holes are massive, the claim is that the black hole can outweigh the stellar component by factors far above local norms. In the nearby universe, a galaxy can have a black hole of 1 billion solar masses, but it usually sits in a bulge of hundreds of billions. Some high redshift reports invert that intuition, implying a central mass that is too large for the visible stellar body. In extreme reports, the black hole to galaxy mass ratio looks tens to hundreds of times larger than today's typical relationship. If those ratios are real, the early universe built central mass faster than it built stars. That would mean the usual co-evolution story is incomplete at early times, or at least out of sequence. It would also mean that the first billion years allowed unusually efficient funneling of gas into the deepest part of a forming galaxy. This is where the central question returns with sharper teeth. Are these real cracks in the Standard Model's growth story, or are we misreading the oldest light and its hidden systematics? The tension is productive because it forces us to examine every step, what we measure, what we infer, and what we assume. A single error in a calibration can masquerade as a revolution, but a persistent anomaly can expose missing physics. To evaluate the tension, we need to explain how distant black holes are detected at all. At high redshift, the black hole is not seen directly, yet its accretion announces itself. A black hole is dark by definition, but an accretion disk is not. When gas spirals inward, gravitational potential energy becomes heat and radiation, and the system can outshine the entire host galaxy. An actively feeding black hole powers an AGN, producing a bright continuum across wavelengths. It also excites surrounding gas, generating broad and narrow emission lines. The continuum often resembles a power law, with a big blue bump in the ultraviolet from the hottest parts of the disk. Around it, dust can reprocess light into infrared, and jets can add radio emission in some objects. Broad lines come from gas moving fast in the deep potential near the black hole. The line widths encode velocity dispersion, and the luminosity hints at the region's size. In a spectrum, these lines are not subtle. Hydrogen, magnesium, carbon, and other ions rise as bright peaks against the continuum. Each line is a tracer of conditions: density, ionization, and motion, all compressed into a feature that can be measured from billions of light-years away. The broadline region is not a single ring. It is likely a complex structure: clouds, streams, perhaps a disk-like component, bathed in intense radiation. The gas responds to the black hole's gravity, but it also responds to radiation pressure and to winds driven off the disk. That mixture is why line shapes can be asymmetric, shifted, or layered, and why interpretation requires care. The standard high redshift mass estimate is the virial method. Measure a broad line width, infer a characteristic radius from luminosity, then compute a mass from v squared times r. The logic is classical mechanics applied to a relativistic environment. Faster motions at a given radius imply a stronger gravitational pull. In practice, the method compresses a complicated geometry into a single number called a virial factor, which carries the uncertainties we cannot directly resolve. This method is calibrated locally using reverberation mapping, where time delays link continuum changes to line response. At high redshift, we usually cannot do that timing experiment, so we borrow the calibration. Reverberation mapping works like sonar in light. The continuum flickers, the gas responds later, and the delay reveals the size of the emitting region. Those local measurements anchor the radius-luminosity relation that high redshift studies depend on. Borrowing that calibration assumes the same physics holds at earlier epochs. It assumes the broadline region scales smoothly with luminosity, even when metallicity, gas density, and accretion structure may differ. It also assumes that the quasar's variability behaves similarly, even though early quasars may be fueled by more turbulent inflows. These are reasonable assumptions, but they are still assumptions. We also assume the broadline region is roughly virialized and has a typical geometry. We assume inclination does not dominate the line width, even though orientation can change what we measure. If the emitting gas has a flattened distribution, then a face-on view yields narrower lines than an edge-on view. That means two identical black holes could produce different inferred masses simply because we view them from different angles. Different lines trace different zones and can yield different masses. MEAN2, C-off and H-beta do not always agree, especially when winds and outflows distort profiles. H-beta is often preferred when available because it tends to be less wind-dominated, but at very high redshift it shifts out of accessible bands. That pushes observers toward ultraviolet lines, which can be more vulnerable to non-virial motions. C-Phi is notorious because it can be shaped by non-virial motions. If a wind broadens the line, the virial mass can be biased high. A strong outflow can also blue-shift the line peak, signaling that the gas is not simply orbiting, but escaping. When that happens, the line width no longer cleanly maps to gravitational velocity, and the mass estimate becomes a blend of gravity and wind physics. Luminosity-based radius estimates also carry assumptions about accretion physics. If early AGN have different spectral energy distributions, the radius-luminosity relation may shift. The ionizing continuum that actually drives line emission is not always the same as the observed continuum used as a proxy. If the spectrum is harder or softer than expected, the broad line region could sit at a different radius for the same measured luminosity. Even the measured luminosity can be uncertain because of dust, lensing, and variability. A magnified or flaring AGN can look intrinsically brighter, inflating inferred size and mass. Dust can both dim and redden the continuum, complicating bolometric corrections that convert a measured band into total power. Variability adds another layer, because a single observation is a snapshot of a system that can change on timescales of days to months in its own frame. Host galaxy masses are also inferred, not weighed. At extreme redshift, the host is faint, compact, and often drowned by the AGN's glare. On screen, this becomes a battle of light profiles, a sharp point spread function for the nucleus, and a soft halo for the galaxy. The decomposition depends on the telescope's optics, the background noise, and the assumed shapes of galaxies that may not resemble nearby ones. Separating host starlight from nuclear light is a modelling problem. If the AGN contributes more to the infrared than expected, the host stellar mass can be underestimated. Hot dust near the nucleus can glow strongly in the near-infrared, exactly where old stars would otherwise dominate. If that dust emission is mistaken for starlight, or if starlight is mistaken for dust, the inferred stellar mass can shift substantially. Stellar mass estimates also rely on population synthesis models. Those models translate colours and spectra into a mass-to-light ratio, which depends on star formation history, metallicity, and the assumed initial mass function. In young galaxies, the light can be dominated by massive short-lived stars that contribute lots of luminosity per unit mass. If the stellar population is younger than assumed, the same light corresponds to less mass, and the host can look heavier than it really is. If the host is underestimated while the black hole is overestimated, the ratio explodes. The most dramatic ratios can therefore be a perfect storm of systematics. A small bias in line width, a small bias in luminosity, and a modest bias in host decomposition can multiply into a headline. This is why cautious papers often emphasize uncertainties even when the central value looks provocative. Yet even after cautious accounting, a real tension may remain. Some early AGNs still appear to host black holes that are too massive for their observed stellar content. The significance is not only the ratio itself, but the pattern across multiple objects and surveys. If the effect persists with better data, it becomes harder to dismiss as a statistical fluke. The next step is to ask why rapid growth is difficult under standard assumptions. The obstacle is not imagination, it is a limit set by radiation. When gas falls into a black hole, it does not simply disappear quietly. It heats, shines, and pushes back, and that pushback can regulate the inflow. The Eddington limit is the balance point where outward radiation pressure on ionized gas matches inward gravity. Above that luminosity, steady spherical inflow is pushed back. The key interaction is between photons and electrons, mainly through Thomson scattering, which couples radiation to plasma. In simple terms, too much light creates too much pressure, and the inflow chokes itself. Accretion at the Eddington rate implies an exponential growth timescale. With typical radiative efficiency, the e-folding time is tens of millions of years. The timescale is often called the Salpeter time, and it depends on how much of the infalling mass is converted into radiation. If the disk is efficient, it shines brightly but grows more slowly, because more mass energy leaves as light. Exponential growth sounds fast, yet the early universe is faster. Starting from a stellar mass seed, you need many e-foldings to reach 1 billion solar masses. Each e-folding multiplies the mass by about 2.7, so the climb from 100 to 1 billion is a long staircase. The arithmetic becomes unforgiving when the clock is set by cosmic expansion. At redshifts above 7, the time available can be less than 1 billion years. Any interruptions in fueling, any feedback-driven gaps, and the arithmetic quickly fails. The early universe is not a quiet laboratory, and accretion is not a smooth pipeline. Gas must lose angular momentum, avoid being blown out, and reach the centre repeatedly, even as stars and supernovae stir the same reservoir. The simplest seed scenario begins with population 3 stars. Metal-free stars may form massive remnants, leaving black holes of tens to hundreds of solar masses. In the first star-forming mini-halos, cooling is limited, which can favour very massive stars compared to later epochs. When such stars die, some may collapse directly into black holes, while others may explode and leave nothing, depending on their mass range. Those seeds are plausible, yet they start small. To reach supermassive scales quickly, they must accrete efficiently and almost continuously. That requirement is not just high accretion, but sustained high accretion across many dynamical times. It also implies that the environment must keep delivering cold gas to the centre, even while the growing black hole begins to heat and ionize its surroundings. But early galaxies are chaotic and feedback is violent. Supernovae and radiation can clear gas, and shallow potentials can starve the central seed. A small halo has a low escape velocity, so an energetic outflow can remove a large fraction of baryons. Even if gas returns later, the duty cycle of accretion may be too intermittent to build a billion solar mass object in time. This is the timing problem in its cleanest form. If the seeds are small and the accretion is limited, the early quasars should not exist in such numbers. The existence of luminous quasars at very high redshift has been a puzzle for years, even before Webb, because it demands both early formation and rapid growth. Webb intensifies the puzzle by hinting that some black holes are not merely present, but disproportionately large relative to their hosts. So the field maps competing solutions, each shifting a different assumption. Some solutions change the seed mass, some change the accretion mode, and some change what we think we observed. The structure of the debate is revealing. It is not one problem, but a chain of linked steps. If any step is altered, seed, fuel, efficiency, geometry, selection, the final mass can change dramatically. First, direct collapse black holes propose bigger starting points. Under special conditions, pristine gas can collapse nearly monolithically into a black hole of 10,000 to 1 million solar masses. The idea has roots in earlier theoretical work on massive objects and gravitational instability, but it gained traction as the timing problem sharpened. A larger seed reduces the need for extreme, uninterrupted accretion. The conditions are demanding because gas usually fragments into stars. To avoid fragmentation, the gas must stay warm and resist forming many small clumps. Fragmentation is driven by efficient cooling, which allows gas to collapse into many dense pockets. If cooling is suppressed, the collapse can remain coherent, feeding a central object rather than a cluster of ordinary stars. A strong Lyman Werner ultraviolet background can suppress molecular hydrogen, removing a key coolant. Rapid inflow and low metallicity can also keep the collapse coherent. Molecular hydrogen is crucial because it cools gas below 10,000 Kelvin, enabling fragmentation in small halos. If Lyman Werner photons dissociate H2, the gas remains hotter and the gene's mass stays large, favouring a single dominant collapse. In some models, the collapsing object passes through an intermediate stage. It may form a supermassive star or a quasi-star, where a black hole grows inside a massive envelope. The envelope can regulate radiation, allowing rapid growth while delaying the moment when feedback blows the system apart. These details vary by model, but they share the same goal: create a head start large enough to beat the cosmic clock. If direct collapse happens, the growth timeline changes immediately. A seed of 100,000 solar masses needs far fewer E-foldings to reach 1 billion. The difference is not subtle, because exponential growth rewards any early advantage. A few 100 million years of Eddington-limited accretion can transform a large seed into a quasar engine, while a small seed might still be struggling to reach intermediate mass. Yet direct collapse must also be rare enough to fit later populations. The universe cannot produce too many massive seeds without overproducing black holes today. This is a constraint that often hides in the background. Whatever solves the early problem must also match the later census. If massive seeds were common, we would expect too many overmassive black holes in local galaxies, unless later evolution somehow erases the evidence. Second, dense star cluster pathways offer another route to heavier seeds. In a compact cluster, repeated stellar collisions can build a very massive star, which then collapses into an intermediate mass black hole. The visual here is almost counterintuitive. Instead of a smooth gas collapse, growth happens through a violent choreography of close encounters. Stars in a dense cluster can sink toward the center through dynamical friction, increasing the collision rate. Runaway mergers require extreme densities and short relaxation times. Early galaxies may provide those conditions in gas-rich nuclear regions. If gas inflow builds a dense stellar system quickly, the cluster can undergo core collapse before massive stars evolve off the main sequence. That timing matters because the most massive stars must still be present to participate in the runaway. This pathway sits between population 3 remnants and direct collapse. It produces seeds larger than stellar remnants, yet smaller than the most extreme direct collapse scenarios. Even a seed of 10,000 solar masses changes the growth arithmetic, especially if it can accrete at high rates during gas-rich phases. The intermediate mass regime is also interesting because it connects two populations that are otherwise hard to bridge observationally. Third, super Eddington accretion challenges the limit rather than the seed. The Eddington limit is strict for simple geometries, yet real disks can behave differently. The classic limit assumes spherical symmetry in steady conditions, but accretion disks are flattened and can be clumpy. In that complexity, radiation can escape along some directions while gas continues to fall in along others. In slim disk models, photon trapping can reduce the effective radiative feedback. Energy is advected inward, so luminosity does not rise as quickly as mass inflow. In other words, the disk can swallow some of its own photons, carrying energy toward the black hole rather than blasting it outward. That reduces the outward pressure that would otherwise halt accretion, allowing the mass inflow rate to exceed the naive Eddington value. Anisotropic emission can also help. If radiation escapes preferentially along poles, gas can still flow in along the disk plane. The system becomes a kind of cosmic lighthouse, bright in some directions and less oppressive in others. This geometry also complicates observations, because what we see depends on viewing angle, and the observed luminosity may not reflect the true mass inflow. Super Eddington growth is often imagined as episodic bursts. Short phases of extreme inflow, separated by quieter periods, can deliver the needed mass without requiring perfect continuity. The early universe may naturally provide such bursts, because mergers and instabilities can dump gas inward rapidly. A black hole could grow in spurts, each one brief on cosmic scales but decisive in cumulative mass. But super Eddington phases must still be physically sustained against feedback and angular momentum barriers. They must also be consistent with observed spectra and variability. If the accretion flow becomes too thick or too turbulent, it may obscure the nucleus or alter the emission lines we use for mass estimates. That creates a subtle loop. The very conditions that enable rapid growth might also change how we infer masses, and that complicates interpretation. Fourth, mergers can accelerate growth by combining black holes. Early galaxies merge frequently, and black hole mergers can add mass without needing accretion for every increment. In hierarchical structure formation, small halos assemble into larger ones, and their central black holes can eventually meet. When they merge, gravitational waves carry away energy, but the remaining black hole retains most of the combined mass. Mergers also reshape the host. They can drive gas inward through tidal torques, triggering both starbursts and accretion episodes. In that sense, mergers are not just a way to add black hole mass directly. They are also a mechanism for delivering fuel, compressing gas, and briefly aligning conditions for rapid growth. Yet mergers alone cannot solve the earliest timing problem. You still need seeds, and you still need gas because mergers require prior growth and prior galaxy assembly. Two small black holes merging do not magically create a billion solar mass object. The merger channel works best as an accelerator, not as the origin, and it depends on the rate at which early structures form and interact. Fifth, coevolution itself may be different at early times. The local relation might not be a birthright, but an outcome reached later. This possibility is conceptually simple but profound, because it reframes the M-sigma relation as a late-time equilibrium. If so, early outliers are not violations but snapshots taken before the system has settled. In that picture, black holes grow first in dense, gas-rich centers. Their feedback then regulates star formation, shaping the bulge and eventually tightening the relation. The early universe provides abundant cold gas, and high densities can drive strong inflows toward the nucleus. If the black hole taps that inflow efficiently, it can gain mass rapidly before the galaxy builds a large, relaxed stellar bulge. Feedback is not only destructive, it is organizing. AGN winds can heat gas, drive outflows and quench star formation, leaving a compact stellar core. On screen, imagine a galaxy with a bright center and a faint disturbed envelope, as if the core survived a storm. The outflow can also compress gas at its edges, potentially triggering star formation in shells while starving the center. If black holes quench early, hosts could remain undermassive while the black hole becomes overmassive. The ratio would be a temporary phase, not a permanent violation. That phase could last long enough to be observable at high redshift, when galaxies are still assembling. Later, the host might catch up through continued star formation, mergers, or the settling of gas into a bulge. This decoupling idea changes what the ratio means. A high ratio would not imply the galaxy is missing mass. It would imply the galaxy's growth was interrupted. The interruption could be caused by feedback, by environmental effects, or by the simple fact that stars need time to form and accumulate. The black hole, by contrast, can gain mass quickly if fuel reaches the center, because it does not need to convert gas into long-lived stellar populations. It also reframes early morphology. Compact, dense hosts might be the survivors of feedback, while extended star formation is suppressed or delayed. Webb's images sometimes show small, bright cores with irregular features, hinting at systems still in formation. The morphology can be a clue, because a disturbed or compact host suggests recent inflow, recent merging, or recent energetic events. But feedback must be modeled carefully because it can also starve the black hole. If outflows clear the nucleus too efficiently, growth stops and the quasar fades. The same wind that quenches star formation can also remove the black hole's fuel supply, turning a bright AGN into a dormant remnant. The balance depends on coupling, how effectively the energy and momentum transfer to the gas that matters for accretion. So the story becomes a balancing act between feeding and self-regulation. Early environments may allow rapid feeding before feedback fully couples to the inflow. There may be a window of opportunity when gas inflow is strong, and the black hole is not yet powerful enough to expel it. If that window opens early, the black hole can leap ahead, and the host must spend the next epoch catching up. Now return to the observational side, because selection effects can mimic a physical trend. We detect what is bright, and AGN are among the brightest beacons in the early universe. A luminous quasar can be seen across cosmic distances, while its host may be invisible without careful subtraction. That asymmetry is not a flaw in astronomy, but it is a bias in what enters our samples. A flux-limited survey preferentially finds the most luminous accretors. That selection biases us toward the most massive black holes, or toward those accreting near their peak. It also biases us toward systems with less obscuration along our line of sight. If dust hides some fraction of the population, then the observed sample may not represent the typical early black hole, but the most exposed and extreme subset. At the same time, the host galaxies can be intrinsically faint or simply hard to measure. The AGN point source can swamp the host, especially in rest frame ultraviolet and optical. Even in the infrared, where starlight can be stronger, the nucleus can dominate through hot dust emission. The decomposition becomes a contest between a bright, compact source and a faint, extended one, and the outcome depends on modelling choices. If the host is missed, the ratio looks extreme. A modest host mass underestimate can turn a mild outlier into a headline. This is why careful studies often report upper limits on host mass rather than precise values. An upper limit can still be informative, but it also leaves room for the host to be larger than currently detected. There is also a surface brightness problem. Early galaxies are compact, and their faint outer light can fall below detection thresholds, especially near a bright nucleus. Cosmological dimming scales steeply with redshift, so extended low surface brightness features are disproportionately hard to see. A galaxy could have a diffuse component that simply vanishes into the background, leaving only the central light visible. Lensing adds another bias. A magnified AGN is easier to find, and lensing can also distort host light in ways that complicate decomposition. A gravitational lens can stretch the host into arcs, while leaving the nucleus relatively compact, confusing automated measurements. Even mild lensing can boost observed flux enough to move an object above a survey threshold, increasing the odds that we detect it. Even without lensing, variability can bias luminosity-based inferences. If a quasar is caught during a bright phase, luminosity and derived radius can be inflated. The broad-line region responds with delays, so a single epoch spectrum can mix a continuum state with a line state that reflects an earlier time. That mismatch can introduce scatter, especially when we push the method beyond the regime where it was calibrated. Orientation can also bias line widths. A disk-like broad-line region viewed edge-on looks broader, producing a larger virial mass than the same system viewed face-on. Orientation also affects observed continuum through obscuration and anisotropy, which can shift both the inferred radius and the inferred velocity. When multiple orientation effects align, they can systematically skew inferred masses upward for some fraction of objects. These biases do not automatically erase the anomaly, yet they caution against overinterpreting the most extreme ratios. The early universe is where our calibrations are most stretched. It is also where small number statistics can mislead, because a handful of spectacular objects can dominate attention. The question becomes whether the outliers are rare curiosities or the visible tip of a broader population. Still, the possibility of genuinely overgrown black holes remains compelling. It suggests the universe can concentrate mass into tiny volumes very early. 1 billion solar masses inside a region smaller than the solar system is an extreme statement about density. It is also a statement about organization, because mass must be delivered to the center without being turned into stars along the way. Black holes are the density endpoints of cosmic structure. If they appear early and oversized, the universe's capacity to assemble mass rapidly may be greater than expected. That capacity depends on the behavior of gas under gravity, on the efficiency of angular momentum transport, and on the timing of feedback. Each of those ingredients is already in our models, but the early universe may combine them in a more aggressive regime than we have tested. That matters for the documentary's theme about how massive space truly is. Space is not only vast in extent, it is vast in what it can build, and in how quickly it can do it. A quasar at high redshift is not just a distant light. It is a monument to rapid assembly, a sign that the cosmos can create deep gravitational wells almost as soon as it creates the first galaxies. If early black holes grew faster than expected, then early gas inflows were more efficient, or early seeds were larger, or early feedback behaved differently. Each option reshapes our picture of the first billion years. Efficient inflows imply that gas could lose angular momentum quickly, perhaps through instabilities or turbulence in dense disks. Larger seeds imply that special formation channels were active early, perhaps in rare environments. Different feedback implies that energy and momentum did not couple to gas in the simple way we often assume. If the anomaly is mostly observational, then Webb is teaching a different lesson. The oldest light is easy to misread, and our mass conversions can manufacture monsters. The lesson would still be profound, because it would reveal how strongly inference depends on calibration. It would also remind us that astronomy often progresses by tightening error bars, not by chasing the most dramatic interpretation. Either way, the central question stays alive. Are we seeing a crack in the standard model, or a crack in our inference chain? The most honest answer is not a verdict, but a set of tests. Better spectra can refine line diagnostics, better imaging can isolate hosts, and larger samples can reveal whether the extremes are typical or exceptional. The chapter's tension should not resolve into a single answer yet. The honest state is a map of possibilities, constrained by data that is still arriving. Webb is not the final word, but it is a powerful new witness, and its testimony is still being cross-examined. Each new observation can shift the balance, either by confirming an outlier or by revealing a hidden bias. We can now summarize the competing explanations in one frame. Oversized early black holes could reflect massive seeds. Super Eddington bursts, dense cluster pathways, rapid coevolution, or selection and modelling biases. The list is not a menu of unrelated ideas, because several can operate together in the same object. A massive seed could still experience super Eddington bursts, and a merger could still trigger feedback that suppresses host growth. The next chapters will test these options with better spectroscopy, better host measurements, and larger samples. The early universe will either normalise or it will keep refusing to fit. If it normalises, the local relation may reassert itself as soon as measurements improve. If it refuses, then the first billion years may demand a revised narrative about how quickly gravity can sculpt the cosmos. A galaxy seen at roughly 290 million years after the Big Bang should, by default, look chemically young. The early cosmos is still cooling from its hot origin, and most baryonic matter remains in its simplest forms. Hydrogen and helium dominate almost everything we can weigh, because Big Bang nucleosynthesis left little else behind. Only trace heavy elements exist at first, contributed by the very first stellar deaths in scattered pockets. Yet Webb's data point to oxygen in that early system, and oxygen is not primordial. Its presence is a statement about time. In astronomical language, oxygen is a metal, meaning any element heavier than helium. That definition sounds odd to chemists, but it is practical for cosmic bookkeeping across many environments. Hydrogen and helium were made in the first minutes, while nearly everything else must be manufactured later. When astronomers say metallicity, they are describing how many stellar generations have already lived, died, and recycled matter. They are also describing cooling physics, because metals give gas more ways to shed heat and collapse. That definition matters because metals are forged, not inherited. The early universe begins with an inventory set by Big Bang nucleosynthesis, a brief window when temperature and density allowed light nuclei to form. In those first minutes, protons and neutrons assembled mostly hydrogen and helium, with a thin residue of lithium and beryllium. Even that residue is fragile because later stellar processing tends to destroy lithium in hot interiors. The periodic table beyond that is essentially blank at the start, waiting for stars to write it. So oxygen at this epoch is a pivot in the story, because it implies a prior history hidden behind the snapshot. It implies that stars formed earlier than the galaxy's observed moment suggests, perhaps in smaller fragments that later combined. It implies that massive stars lived fast, died fast, and enriched their surroundings quickly. It implies that the gas we see has already been processed through stellar interiors, then returned to space. In a universe this young, that recycling loop feels almost rushed, like finding ash before you expect the fire. The shock is not that one massive star can make oxygen, because we understand those nuclear pathways well. The shock is that enough oxygen exists, in enough gas, to register across such an enormous cosmic distance. Detectable oxygen suggests a population, not a single event, because a lone supernova rarely enriches an entire galaxy-scale nebula. It suggests multiple explosions, repeated cycles of formation and death, and rapid dispersal into regions bright enough to be seen. It also suggests that the emitting gas is not pristine inflow alone, but a mixture already touched by earlier stars. Visually, imagine what that means. A faint smudge of light on Webb's detector stretched into a tiny arc by distance and time. The image looks simple, almost minimal, but the physics behind it is not. Then imagine its spectrum, a barcode of peaks and valleys, carrying the chemical memory of stars that no longer exist. The oxygen is not glowing as a simple colour. It is announcing itself through narrow lines, like a signature written in infrared ink. On a plot, those lines rise sharply from the noise, small mountains that say, unmistakably, processed material. To understand why this breaks expectations, we need the basic chemistry engine that runs inside stars. In stellar cores, fusion builds heavier nuclei from lighter ones, but only along pathways allowed by temperature, pressure, and quantum tunneling. Low-mass stars fuse hydrogen into helium slowly, spending billions of years on the main sequence. Later, some proceed to helium burning and beyond, but they do so late and gently, and many never reach the hottest stages. They are important for long-term enrichment, yet they are too slow to explain oxygen this early. Massive stars are different. Hotter cores, higher pressures, and a far more urgent pace. They burn through hydrogen quickly, then move on to helium, carbon, neon, oxygen, and silicon, burning in successive shells. Each stage is shorter than the last, like a countdown accelerating toward collapse. In these stars, helium burning produces carbon and oxygen through well-known nuclear reactions, including the triple alpha process that builds carbon, followed by alpha capture that builds oxygen. The relative amounts depend on reaction rates that nuclear physicists measure in laboratories, because tiny changes in cross-sections echo into cosmic abundances. Later burning stages can build elements up to iron, but oxygen is already abundant by then. Oxygen becomes one of the dominant products of helium burning, and it accumulates in large quantities in massive stellar interiors. When the core eventually collapses, the star's death is not quiet. A core collapse supernova launches shockwaves that tear through the star's layers, ejecting newly made elements into the surrounding interstellar medium. In some cases, the explosion may be asymmetric, carving channels that vent metals more efficiently into the galaxy's outskirts. That ejector becomes the raw material for the next generation of stars, but it is also a chemical dye in the cosmic ocean. Oxygen atoms, once locked in a stellar core, are thrown outward at thousands of kilometers per second. They crash into surrounding gas, heat it, ionize it, and seed it with metals that change how it cools. In a young galaxy, this feedback is both creative and destructive, forming stars while also blowing apart their nurseries. The same event that enriches the gas can also evacuate it, and that tension shapes early evolution. This is why oxygen is a time marker, not merely a composition detail. You cannot have widespread oxygen without prior stellar lifetimes and prior explosions, and those lifetimes are not instantaneous. You also need time for enriched gas to mix with other gas, or at least to dominate the regions producing the observed emission. Chemistry becomes a chronometer that runs alongside the expansion clock, and sometimes it argues with it. When the chemical clock runs fast, we're forced to ask what made it accelerate. The timescales are tight, but not impossible for individual stars. A very massive star can live only a few million years, and some of the most massive can die even sooner. In principle, several generations could fit into 290 million years, especially if star formation began early and proceeded in bursts. The real difficulty is building galaxy-wide enrichment quickly enough to be seen, because production is only the first step. The second step is transport, and transport is messy in shallow gravitational wells. Enrichment is not only about making oxygen, it is about distributing it into the gas that actually emits the lines Webb measures. Supernovae must occur in sufficient numbers to raise metallicity measurably, and the metals must reach ionized regions that glow. If oxygen stays locked in dense, cold clumps, it may not contribute strongly to the nebular emission lines. Outflows, turbulence, and radiation-driven pressure must spread oxygen to the diffuse gas we can observe. Mixing is not instantaneous, because metals can remain clumpy for tens of millions of years in simulations. In standard models, early star formation is bursty, and feedback is disruptive in small halos. The first galaxies live in shallow gravitational wells, where a few supernovae can expel a large fraction of the available gas. Winds can evacuate the very material needed for continued enrichment, and the system can temporarily starve itself. Mixing can also be inefficient when the galaxy is fragmented, rapidly evolving, and constantly replenished by fresh inflow. Fresh inflow matters because it can dilute metals even as stars try to concentrate them. So a chemically mature signature, this early, strains the default pacing, even if it does not break it outright. It forces us to ask whether our assumptions about early star formation are too conservative. It also forces us to ask whether we are seeing a special case, a rare, intense system, rather than a typical galaxy of its era. Webb's early targets are often the brightest, and brightness can be a kind of selection bias. The universe may contain many faint, chemically young systems that simply fall below detection. Webb's role is not that it sees oxygen directly as a colour in an image. Webb sees spectra, and spectra are where elements reveal themselves with precision. Every atom and ion has allowed transitions at specific energies, determined by quantum mechanics and selection rules. Those transitions appear as emission or absorption lines at precise wavelengths, and the pattern is as distinctive as a fingerprint. In ionized nebulae, oxygen often appears as forbidden lines, transitions that are rare on Earth but common in thin cosmic gas. At high redshift, those wavelengths are stretched by cosmic expansion, which shifts them toward longer wavelengths. A line emitted in the ultraviolet or optical can be shifted into the near-infrared by the time it reaches us. That is exactly Webb's design space, and it is why spectroscopy is central here. The telescope becomes a time machine only because it is an infrared spectrograph with extraordinary sensitivity. Even the detectors are tuned for faint photons that have been travelling since the universe was still assembling its first complex structures. The key difference is between photometric hints and spectroscopic confirmation, and that difference shapes how confident we can be. Photometry measures flux through broad filters, then infers features indirectly from colours. Strong emission lines can masquerade as continuum bumps inside those filters, making a galaxy appear unusually bright in one band. That can mimic a spectral break, which can mimic a higher redshift, which can distort the inferred age. This is why early claims often arrive with caveats, and why follow-up spectroscopy becomes decisive. Spectroscopy disperses the light and separates line from continuum, reducing ambiguity. It turns a broad, suggestive colour into a measured wavelength and a measured line profile. With spectroscopy, oxygen is not guessed. It is identified by its pattern of lines and their relative spacing. The observed wavelengths determine a redshift, and the line ratios constrain physical conditions inside the ionized gas. Line widths can even hint at dynamics, because turbulence and outflows broaden features in ways that carry physical meaning. Multiple lines can cross-check each other, making the identification harder to dismiss. In practice, astronomers look for consistent sets of features, not a single isolated peak. They test whether alternative identifications would require implausible conditions or inconsistent redshifts. The claim becomes less about templates and more about measured features, although interpretation still requires modelling. That modelling is where the mystery deepens, because extreme early galaxies may not behave like local calibrators. Visually, the spectrum itself becomes a landscape. A bright line rises like a mountain ridge above the baseline, and its position is shifted far from where it would sit in a nearby galaxy. Labels appear: rest wavelength, observed wavelength, inferred redshift, while the narrator reminds us that the shift is the universe expanding. The oxygen line is not just a peak, it is a timestamp. In a single glance, the plot links atomic physics to cosmic history. Still, oxygen detection is not a single number, and interpretation is conditional. Astronomers infer metallicity by comparing line strengths to models of ionized gas, often using photoionization codes that simulate how radiation interacts with a nebula. Those models depend on electron temperature, because hotter electrons collide more energetically and change excitation rates. They depend on electron density, because dense gas can suppress certain transitions through collisional de-excitation. They also depend on geometry, because a clumpy nebula can hide dense regions that contribute little light. They also depend on the ionizing radiation field, which is shaped by the stellar population's age and mass distribution. A very young starburst produces a harder spectrum, rich in high-energy photons that can doubly ionize oxygen. Dust complicates the picture by absorbing ultraviolet and optical light, then re-emitting it in the infrared. Even a small amount of dust can tilt line ratios and alter the apparent continuum, especially in compact star-forming regions. Dust is itself a metal product, which makes the early appearance of dust another quiet pressure on the timeline. Metallicity is often expressed relative to the Sun, even when the environment is nothing like the Milky Way. A value like 1/10 solar sounds simple, but it hides modelling assumptions about abundance patterns and ionization structure. At high redshift, those assumptions are stretched by unfamiliar starbursts, extreme radiation fields, and possibly different element ratios. The same line ratio can be produced by different combinations of metallicity and ionization, and that is where the tension lives. The chronometer is real, yet the dial can be hard to read. This is the degeneracy problem, and it is central to the chapter's mystery. A hard radiation field from very young, massive stars can mimic some low metallicity signatures because it changes which ions are present. High ionization parameters can boost certain oxygen lines while suppressing others, shifting the diagnostic diagrams. Dust can selectively absorb and scatter, altering apparent line strengths and changing how we interpret the continuum. Even the escape of ionizing photons can matter, because leakage changes the nebula's ionization balance. So the question becomes precise, and it is more subtle than a headline. Is the galaxy truly metal enriched, or are we reading extreme physical conditions as enrichment? Webb's spectra narrow the possibilities, but they do not eliminate them, because the models are only as good as their assumptions. The chronometer is powerful, yet it must be calibrated against an environment that may be unlike anything nearby. When the environment is unprecedented, even a fingerprint can be misinterpreted. Even with degeneracies, oxygen still implies prior stellar processing, because oxygen does not appear without stars. The remaining debate is about degree and speed, not about existence. How much oxygen is present and how quickly did it accumulate in the gas we see? That debate points to several physical explanations that keep LCDM intact, at least for now, while still acknowledging the strain. The goal is not to defend a model by force, but to understand what the data demand. First is early onset of star formation, which reframes the observed galaxy as a late chapter in its own life. The system we observe at 290 million years may not be the beginning of its story, because smaller progenitors can form stars earlier. In hierarchical growth, fragments merge, and their stars and metals merge with them. The oxygen we detect could be inherited from those earlier pieces, already enriched before the final assembly. In that picture, Webb is catching the system after it has already lived through a hidden prologue. This explanation shifts the question backward in time. If the oxygen is inherited, then star formation must have begun even earlier, perhaps tens of millions of years sooner. That pushes us toward the era when the first halos cooled and condensed gas efficiently. It also pushes us into an environment shaped by the first radiation backgrounds, where ultraviolet photons can heat gas and inhibit collapse in the smallest halos. The earlier stars do not merely illuminate their neighborhoods, they regulate who gets to form next. Second is a top-heavy initial mass function in the earliest populations, meaning a higher fraction of massive stars than we see today. If early star formation produced more massive stars, metal yields rise quickly because massive stars are efficient oxygen factories. They also explode promptly, returning metals to the gas on short timescales. The same total formed mass would enrich the surrounding medium more efficiently, and the enrichment would happen early. Historically, this idea echoes older debates about population 3 stars, which were long expected to be unusually massive in pristine gas. A top-heavy IMF also changes the light we see, which loops back to earlier chapters about brightness and inferred mass. Massive stars emit enormous ultraviolet output, and they power strong nebular emission lines in surrounding gas. That can make galaxies appear brighter and more line-dominated for a given stellar mass. It can reduce inferred stellar masses while increasing inferred enrichment, because the same observed flux corresponds to fewer long-lived, low-mass stars. It also changes supernova statistics, because clustered massive deaths can behave differently than isolated explosions. Third is unusually efficient star formation in dense halos, where gas can collapse rapidly and sustain intense star formation. If gas inflow is rapid and continuous, the system can keep fueling new stars despite feedback. High densities shorten freefall times, raising star formation rates and producing clustered supernovae. In that regime, feedback may not fully shut down the cycle, because fresh gas keeps arriving along filaments. The galaxy becomes less like a gentle nursery, and more like a furnace that keeps being fed. This is where the visuals of the early universe become dynamic rather than static. Cold streams of gas flow along the cosmic web, feeding a compact node where stars ignite in bursts. Supernovae flare like brief beacons, driving expanding shells into surrounding gas. The galaxy is small in size yet violent in energy, and that violence can accelerate chemical evolution. In close-up, the scene is turbulent. Shocks, ionization fronts and cavities carved by radiation. Fourth is mergers that concentrate enriched gas and trigger starbursts. When small systems collide, gas can be driven inward and compressed, raising densities and igniting rapid star formation. Supernova rates spike, and metal production accelerates in a short window. Mixing can also be enhanced by merger-driven turbulence, which stirs metals into a larger volume and brings enriched gas into the ionized regions that produce strong lines. In a young universe where interactions are frequent, a merger can be a shortcut through the chemical timeline. Fifth is efficient outflows that spread metals beyond the star-forming core, which sounds counterproductive but can change what we observe. Winds can carry oxygen into surrounding gas that later becomes ionized and visible, especially if the galaxy sits in a growing ionized bubble. The galaxy can look chemically mature because metals are widely distributed, not because the core is old. In other words, the oxygen may be telling us about transport as much as production. The signature could be written in the halo, not just in the center. Each explanation has a cost, and the costs are where the science becomes interesting. Early onset demands star formation in even earlier, smaller halos under harsh radiative backgrounds. A top-heavy IMF must not break later chemical evolution constraints, because today's galaxies carry fossil records in their element ratios. Extreme efficiency must coexist with feedback that simulations already struggle to model, especially when resolution limits hide small-scale turbulence, and mergers must occur at the right time, in the right numbers, without overproducing stars compared with later observations. There is also a deeper physical point hiding underneath these options. Metals change cooling, and cooling changes star formation, creating a feedback loop that can accelerate evolution. Oxygen and other metals provide additional ways for gas to radiate away energy through line emission. Once a small amount of metals exists, gas can cool more efficiently, fragment more readily, and form stars more quickly. In that sense, early oxygen can be both a consequence and a catalyst. A small chemical head start can compound, turning modest early enrichment into rapid later growth. Now widen the lens to reionization, because oxygen is not only a chemical clue, it is also a clue about radiation. Reionization is the phase when the first luminous sources ionize the intergalactic medium, transforming neutral hydrogen fog into a transparent ionized plasma. Before reionization, ultraviolet light is easily absorbed by neutral hydrogen, and the universe is more opaque. After reionization, photons travel farther, and the cosmic web becomes more visible. The shift is not just scientific, it is visual, like a fog lifting from a landscape. The timing and speed of that transformation remain active questions, constrained by multiple lines of evidence. The cosmic microwave background encodes an integrated measure of how much ionized gas existed along the line of sight. Quasar spectra at later times show the fading of the gun, Peterson trough as the neutral fraction drops. Galaxy surveys suggest a gradual patchy process where ionized bubbles grow and merge over hundreds of millions of years. The patchiness matters because it means the universe did not reionize everywhere at once. Early oxygen implies early intense star formation, which implies abundant ionizing photons. Massive stars emit the ultraviolet radiation that drives reionization, and their short lifetimes mean the ionizing output is front-loaded. If galaxies are enriching quickly, they may also be ionizing quickly because both processes rely on massive stars. Oxygen becomes indirect evidence about how fast the cosmic fog cleared, even if it is not a direct measurement of ionization. It invites a question that hangs in the background. Are we underestimating how many ionizing photons escaped early galaxies? But reionization is not uniform, and that matters for interpretation of spectra. Ionized bubbles grow around galaxies and merge over time, creating a patchwork of transparent and opaque regions. A galaxy inside a large ionized bubble can show different spectral signatures than one embedded in neutral surroundings. The environment can shape what lines escape and what continua are absorbed, especially on the blue side of Lyman alpha. Even the damping wing of neutral hydrogen can reshape what we think we are seeing, turning environment into an observational filter. So oxygen at 290 million years is not an isolated anomaly. It is a node in a network of implications. It connects to the broader question of early luminous efficiency and how quickly galaxies turned gas into stars. It connects to whether the first galaxies were common enough and bright enough to reionize the universe on schedule. It connects to whether our models undercount early star formation or underestimate how porous early galaxies were to ionizing radiation. And it raises a quiet, unsettling observation. Chemistry and transparency may be advancing together, faster than expected. At this point, the documentary's central question tightens, and the tone becomes more investigative. Are Webb's early universe discoveries real cracks in the standard model, or are we misreading the oldest light? Chemistry is harder to fake than brightness, because elements have discrete spectral fingerprints. Yet chemistry is still interpreted through models, and models can be surprised by extreme conditions. The tension shifts from mass estimates to physical history, and from photometric ambiguity to spectroscopic argument. The evidence feels firmer, but the interpretation feels more exposed. Now pivot from chemical clocks to spatial scales, because the same early universe hosts another kind of surprise. The cosmic web is the large-scale structure of matter, shaped by gravity acting on primordial fluctuations. It is a network of filaments, nodes, and voids, where dark matter provides the scaffolding and gas follows the gravitational wells. Galaxies form in the densest nodes where filaments intersect, fed by streams of inflowing material. In simulations, those filaments are not decorative. They are the highways that deliver fuel. In LCDM, the web grows from tiny initial perturbations measured in the cosmic microwave background. Those perturbations are close to Gaussian, meaning extreme peaks are rare in a predictable way. Over time, gravity amplifies them, and the distribution of structures evolves from subtle ripples to pronounced filaments. At early epochs, the biggest coherent features should be limited by the time available for growth, because gravity needs time to pull matter together. The universe can be dense, but it is still young, and youth sets a speed limit. That creates statistical expectations for maximum sizes at a given redshift. You can have rare peaks, but their abundance and scale are constrained by the initial power spectrum and by the growth history. When observers report a structure that seems too large too early, it raises a familiar question. Is this a true outlier, or a measurement artifact that disappears with better data? The history of cosmology is full of early impossible objects that became ordinary once uncertainties were understood. The reported tension is not always a single monolithic object, but an apparent association across the sky. It can be an overdensity of galaxies aligned across a wide region, suggesting a filament or a node of unusual richness. It can be a filamentary feature inferred from clustered redshifts, where multiple galaxies appear to share similar distances. It can be a proto-supercluster candidate emerging before the universe should have assembled such coherence, at least in typical realizations. The key word is proto because we are watching the blueprint, not the finished city. Before invoking new physics, the first suspect is projection, because the sky is a two-dimensional canvas. A two-dimensional view can stack unrelated structures along the line of sight, making chance alignments look like connected features. Photometric redshift uncertainties can smear distances and create false associations, especially when strong emission lines distort colors. Even spectroscopic samples can be incomplete, and incompleteness can make patterns look sharper than they are. A handful of confirmed redshifts can anchor a story that the missing data would soften. Selection artifacts can also manufacture apparent largeness, and early surveys are especially vulnerable. Observations often target regions with known overdensities, or fields behind lensing clusters that magnify faint galaxies. Detection thresholds favor bright galaxies that may cluster in biased environments, because bright galaxies are not randomly distributed. If the sample is not uniform, the inferred structure can be exaggerated, and the too large claim can be premature. Lensing in particular can stretch and brighten sources in ways that complicate how we map them onto three-dimensional space. Cosmic variance is the honest version of the same problem, and it is unavoidable in small fields. Early surveys cover limited areas, and limited areas can land on rare peaks by chance. A rare peak is allowed by the model, but it is not typical, and typical is what our intuition expects. The question becomes whether Webb is repeatedly finding rare peaks, or whether early fields were simply lucky, because luck is a statistical parameter too. If we keep rolling the cosmic dice and keep seeing sixes, we eventually ask whether the dice are weighted, or whether we are only looking where sixes are easiest to notice. If the structure is real and not an artifact, the implications widen quickly, because large-scale structure is a cosmological observable. It could suggest more power on certain scales in the initial conditions, meaning stronger primordial fluctuations at those wavelengths. It could suggest non-Gaussianity that increases the probability of extreme peaks without changing the average. It could suggest modified growth rates that accelerate structure formation, allowing filaments and nodes to mature earlier. Each option is a different way of changing the early blueprint while trying to preserve the later city. Non-Gaussianity sounds abstract, but it has a concrete meaning in probability. It changes the tail of the distribution where rare objects live, and the tail is where too early claims are born. A small change in the tail can produce many more extreme peaks, even if the bulk of the distribution looks unchanged. Those peaks then seed earlier, larger structures without necessarily disrupting the model's success elsewhere. In other words, the universe can look normal on average while still producing more early giants than expected. Modified growth rates can come from changes in the dark sector, and the dark sector is where LCDM hides most of its unknowns. Early dark energy can alter expansion and the time available for growth, changing how quickly overdensities deepen. Interacting dark matter can change clustering behavior, affecting how small structures merge into larger ones. Modified gravity can change how strongly matter responds to curvature, changing collapse times without changing initial conditions. Each idea is tempting because it offers a dial to turn, yet each dial is constrained by other measurements. Each of these ideas is constrained by the CMB and by later structure surveys, which is why the community treats them cautiously. The standard model fits a wide range of data with remarkable precision, from acoustic peaks to galaxy clustering to lensing. Any modification must thread a narrow path between early anomalies and late-time successes. That is why these claims are framed as tensions, not revolutions, even when they sound dramatic. The burden of proof is high because the model's track record is strong. Still, the pattern across chapters is hard to ignore because the anomalies rhyme. Massive galaxies appear early, black holes appear overgrown, oxygen appears surprisingly soon, and large structures may appear too coherent. Each line of evidence can be softened by systematics, and each can be defended with astrophysical flexibility. Together they press on the same timeline, as if the early universe is consistently more productive than expected. The question is not whether any single clue is decisive, but why so many clues point in the same direction. That timeline is built from distances, ages, and an expansion history, and it is only as strong as its conversions. Redshift becomes distance through cosmology, and distance becomes luminosity, and luminosity becomes mass and star formation rate. When those pieces do not cohere, the most basic number becomes suspect, because the clock itself may be miscalibrated. The universe's expansion rate sets the conversion from redshift to time, and time is what chemistry and structure are arguing about. If the conversion is slightly off, the disagreement can masquerade as impossible astrophysics. This brings us back to the documentary's underlying hinge, which has been tightening with each new clue. If Webb-era observations keep implying that the early universe did more in less time, either astrophysics was more efficient, or the clock is slightly off. A slightly different expansion history can shift ages at high redshift, even if it barely changes the present-day universe. That shift can be tens of millions of years, which matters when massive stars live only millions. In this era, a few tens of millions is not a footnote. It is multiple stellar lifetimes. The oxygen detection therefore becomes more than a chemical curiosity. It becomes a stress test for the entire inference chain from photons to history. It asks whether our models of early star formation, feedback and mixing are incomplete, especially under extreme densities and radiation fields. It also asks whether the cosmological parameters that set the clock are as settled as we claim, given persistent disagreements elsewhere. Oxygen, in this context, is a stopwatch reading that does not quite match the schedule, and once a stopwatch disagrees, we have to check the clock on the wall. We can hold both possibilities without choosing yet, and that uncertainty is part of the mystery. Webb may be revealing extreme but allowed corners of LCDM, amplified by selection and small samples. Webb may be revealing that early baryonic physics is more aggressive than our simulations capture, with faster cooling, stronger clustering, and more efficient recycling. Or Webb may be hinting that the background cosmology that maps redshift to time needs revision, even if only slightly. The most unsettling possibility is not that we are wrong, but that we are only partly right. The chapter ends by tightening toward the climax, because the clues are converging. Chemistry, structure, and timing are converging on the same pressure point, and the pressure is not just academic. If oxygen appears too early and the Webb looks too large, then the universe is not only vast in space, it is vast in the gap between our expectations and what the oldest light implies, and that gap demands an explanation. The oldest photons are not merely ancient, they are argumentative. H0 is the present expansion rate, stated in kilometers per second per megaparsec, and it is deceptively simple. It tells you how fast space stretches today, how many kilometers per second of recession you expect for every megaparsec of distance. Nearby, where gravity has not yet fully tangled motions into chaos, redshift and distance line up into a clean relation. Farther out, that same number becomes a conversion factor between what we observe and what we infer. Change. HEO and the universe's biography changes, even when the sky looks identical. On screen, it helps to imagine a cosmic dashboard. One dial reads redshift, another reads distance, and a third, H0, translates between them. When that dial turns, the implied age of the universe turns with it, because expansion rate and cosmic time are coupled. A higher h0 generally implies a younger universe, because the current pace suggests less time has elapsed since the beginning. A lower h0 implies more time, more breathing room for galaxies, clusters, and black holes to assemble. Historically, this number has never been calm. Edwin Hubble's original estimate in the 1920s was wildly high by modern standards, partly because the distance scale itself was miscalibrated. Over decades, astronomers revised stellar populations corrected for dust, and learned that some standard candles were not one species at all. The expansion rate fell, then stabilized, and eventually became precise enough that disagreements could no longer hide in broad error bars. The Hubble tension is what happens when precision becomes sharp enough to cut. The Hubble tension is a precise mismatch between two ways of measuring h0, and it is now measured in percent rather than factors. One method measures the late universe directly through the distance ladder, using objects close enough to calibrate carefully. The other infers h0 from the early universe using the cosmic microwave background under LCDM, the standard model of cosmology. Both methods are internally consistent, both are carefully audited, and yet they point to different present-day speeds. In the local ladder, the goal is geometric calibration, then stepwise extension outward, always trying to avoid assumptions about cosmology. Parallax sets absolute distances to nearby stars, increasingly through Gaia, by measuring tiny shifts in apparent position as Earth orbits the Sun. Those shifts are measured in microarc seconds, angles so small they resemble seeing a coin on the Moon. From those anchor stars, Cepheid variables extend the scale to nearby galaxies through the period. Luminosity relation. Type Ia supernovae then carry that calibration deep into the Hubble flow, where peculiar motions average out and expansion dominates. Visually, the ladder is a literal staircase of light. First, nearby stars with measured parallaxes glow against a dark background. Their distance is tagged like labels in a planetarium. Then the view widens to spiral galaxies, where Cepheids pulse like slow beacons embedded in luminous arms. Finally, the camera pulls back to show supernovae, brief, brilliant flares that outshine entire galaxies and can be seen across billions of light years. Parallax is the bedrock because it is geometry, not astrophysical modelling, although even geometry has complications at this precision. Gaia must correct for spacecraft motion, detector behaviour, and subtle biases that can shift the parallax zero point. A microarc second offset sounds trivial, yet it can move the inferred distance scale by a fraction of a percent. That fraction then propagates upward through every rung. In a chain where each step multiplies the next, small biases do not stay small. Cepheids add power because they are bright and regular, and their physics is understood in broad strokes. These stars swell and contract due to a pulsation mechanism tied to helium ionization, which traps heat and drives periodic expansion. The period of pulsation correlates with intrinsic luminosity, so the rhythm becomes a distance indicator. But Cepheids are not identical bulbs. Their brightness depends subtly on metallicity, on temperature, and on how their light is filtered through dust. Type Ia supernovae sit on the next rung because they are extraordinarily luminous and relatively uniform after standardization. They are thought to arise from white dwarfs approaching a critical mass through accretion or merger, triggering a thermonuclear runaway. The light curve shape and colour can be used to correct their peak brightness, turning them into standardizable candles. Yet the details of progenitors, host environments, and dust laws matter. A small drift in how supernovae behave with host galaxy properties can masquerade as a cosmological signal. The ladder measures distances and recession velocities in the nearby universe, then fits a slope. That slope is h0, and it is meant to be model light, because it relies on geometry and empirical calibration. The ladder does assume corrections for dust, metallicity, crowding, selection, and instrument cross-calibration. It also assumes that the local universe is not dramatically unrepresentative, even though it contains voids, clusters, and bulk flows. The aim is to sample enough volume that local quirks average out. On a plot, the ladder's logic looks almost humble. Points scatter around a line, each point a galaxy with a measured distance and redshift. The line's slope is the expansion rate, and the uncertainty is the thickness of the band around it. But beneath that simple line is a deep stack of astrophysical and instrumental decisions. Each decision is tested, retested, and compared across teams, because the tension is now too large to ignore. In the early universe method, The CMB does not measure H0 directly, and that distinction is crucial. It measures a pattern of temperature and polarization anisotropies imprinted when the universe became transparent. Those patterns include acoustic peak positions and heights, which encode the sound horizon and matter content. Before recombination, photons and baryons formed a tightly coupled plasma, and pressure waves propagated through it. When the universe cooled enough for electrons and protons to form neutral hydrogen, photons decoupled and streamed freely, carrying a frozen snapshot of those waves. Visually, the CMB is a glowing sphere around us, mottled with tiny hot and cold spots. The camera can drift across that map, then zoom into a power spectrum where peaks rise like a mountain range. Each peak corresponds to a harmonic of the early universe sound waves. The first peak sets a characteristic angular scale, and that angle is compared to a physical scale, the sound horizon, to infer distances. It is a cosmic ruler, but it is a ruler that must be computed. Under LCDM, those parameters imply a specific expansion history, which implies H0 today. The model includes cold dark matter, ordinary matter, radiation, and a cosmological constant like dark energy. It also includes the physics of recombination, neutrino behavior, and the relationship between matter density and curvature. When the CMB fixes the matter density in the angular scale of the sound horizon, the model determines how fast the universe must be expanding now. The inference is indirect, but it is tightly constrained. The CMB inference is powerful because it is global and high precision, and because it is measured on the larger scales we can observe. It is also conditional because it assumes a model connecting recombination physics to late-time expansion. If the model is slightly wrong, the inferred H0 can shift without obvious alarms. The CMB can still look perfectly fit because the model can compensate by adjusting correlated parameters. That is the unsettling part. Good fits do not guarantee correct assumptions. The tension is not a rounding error, and it has survived years of refinement, reanalysis, and cross-checking. The ladder tends to land near the low to mid-70s in kilometers per second per megaparsec. The CMB under LCDM tends to land near the high 60s. The gap is several kilometers per second per megaparsec, large compared to quoted uncertainties. In statistical terms, it has hovered in the territory where physicists start to suspect either hidden systematics or new physics. This is why the tension is a mystery engine, not a technical footnote. Two measurements describe one universe, yet they disagree on its current speed. If one is right, the other is missing something real, either a subtle bias in a measurement chain or a missing ingredient in the cosmic recipe. The tension forces a question that is both simple and profound. How can the same cosmos have two present-day expansion rates? The disagreement persists across multiple datasets and analysis choices, which is why it refuses to fade. Different Cepheid samples and different supernova compilations still cluster near a higher H0, even when teams use different cuts and different statistical treatments. Different CMB analyses still cluster near a lower H0 when LCDM is enforced, even when foregrounds and instrument systematics are modelled in multiple ways. The mismatch has become a pattern, not a single controversial paper. Patterns are harder to dismiss because they survive the removal of any one brick. Webb matters because it attacks the ladder's most fragile links, and it does so with a different set of eyes. Cepheids are bright, but they live in dusty, crowded star-forming regions where confusion is easy. In optical bands, dust reddening and extinction can bias the inferred luminosity, and the correction depends on the dust law. In crowded fields, blended stars can inflate a Cepheid's measured brightness, making it appear closer than it is. A Cepheid that looks slightly too bright pushes the distance scale down and H0 up. Picture a distant galaxy as Hubble sees it in visible light. The spiral arms are luminous, but they are also busy. Knots of star formation, lanes of dust and overlapping point sources. A Cepheid sits in that clutter, pulsing steadily, while nearby stars smear into the same pixel footprint. The measurement becomes a kind of forensic photometry, separating one heartbeat of light from a crowd. Webb's infrared resolution reduces both problems at once, and that combination is why its data are so valuable. Infrared light penetrates dust better, lowering extinction corrections and reducing sensitivity to uncertain reddening laws. Webb's sharper point spread function reduces crowding and blending in distant host galaxies, because it can separate sources that were previously merged. That improves the calibration of Cepheid distances, which improves the supernova anchor. It is not merely better images, it is cleaner inference. Webb also helps cross-calibrate instruments and bandpasses, which is a quiet but central vulnerability of the ladder. The ladder depends on consistent photometric systems across Hubble, ground surveys, and now Webb, and consistency is hard across decades of detectors. Small zero-point shifts can propagate into percent-level distance errors. Percent-level distance errors become kilometre per second per megaparsec shifts in H0. The danger is not a dramatic mistake. The danger is a tiny offset repeated everywhere. In practice, cross-calibration means comparing how the same star looks in different filters with different detectors under different backgrounds. It means tracking nonlinearity, saturation behaviour, and subtle colour terms. It means building a bridge between datasets that were never designed to be combined. Webb stability and infrared sensitivity make that bridge sturdier, but the bridge still has joints. Those joints are where cosmologists look for cracks. The key point is that systematics can move H0, but they have not erased the discrepancy. Web-based C-FID work can nudge the ladder value modestly, and it can tighten uncertainties by reducing scatter. It can expose hidden biases in older data, especially those driven by crowding. Yet the tension remains when those improvements are folded in. The result is not a dramatic reversal, but a stubborn persistence. That persistence forces a fork in interpretation, and neither branch is comfortable. Either the local ladder is biased high by unrecognized systematics, despite years of scrutiny, or the early universe inference is biased low because LCDM is incomplete, despite its remarkable success elsewhere. The fork is not philosophical. It is quantitative, and it is now sharp enough to guide entire research programs. If the local H0 is right, then something about pre-recombination physics is off, and the CMB's ruler must be recalibrated. The CMB primarily constrains the sound horizon, a standard ruler set by early plasma physics. The sound horizon is the distance a sound wave can travel in the photon, baryon fluid before recombination, and it depends on the expansion rate and the composition of the universe. If that ruler is smaller than LCDM predicts, the inferred H0 rises. Many proposed fixes therefore try to shrink the sound horizon without ruining the CMB fit. To see why, imagine the CMB peaks as angles drawn on the sky. The observed angle is fixed by data, so if the physical ruler is smaller, the distance to the CMB surface must also be smaller. In LCDM geometry, a smaller distance to that surface typically implies a higher H0 today, because the model adjusts the expansion history to match. The logic is tight, almost mechanical, and that is why the sound horizon has become the battlefield. Change the ruler, and the inference shifts. If the CMB inferred H0 is right, then local measurements must hide correlated errors, and those errors must be persistent across teams. The ladder is a chain, and a small bias at one step can masquerade as new physics. The hard part is that different teams using different data still converge on similar high values. That convergence suggests either a shared hidden assumption or a shared astrophysical complication. It also suggests that the solution, if systematic, may be subtle rather than obvious. To break the stalemate, cosmology leans on independent cross-checks, and these methods are now central characters. These approaches bypass some ladder steps, or avoid the CMB model dependence, and they often rely on different physics. They are not yet perfect arbiters, but they are becoming decisive. Each one is a separate way of asking the same question. How big is the universe's present-day stretch? Time-delay gravitational lensing uses quasars lensed into multiple images, a phenomenon predicted by general relativity and confirmed across the sky. Light takes different paths through curved space-time, producing measurable arrival time delays when the quasar varies. Those delays depend on the lens mass model and on cosmological distances, which depend on H0. The method is independent of key feeds, but it is sensitive to lens modelling and line-of-sight structure. A galaxy group along the line of sight can subtly change the inferred geometry. Visually, lensing is one of the universe's most elegant illusions. A single quasar becomes a cross or a ring around a foreground galaxy, and each image flickers with the same intrinsic variability. The flicker arrives out of sync like echoes in a canyon, because each path has a different length and a different gravitational delay. Measuring those echoes requires years of monitoring and careful mass reconstruction. The reward is a distance scale rooted in relativity. The tip of the red giant branch uses a different kind of standard candle, and it comes from stellar evolution rather than pulsation. Low-mass stars climb the red giant branch until helium ignition occurs in their cores, producing a fairly predictable luminosity at the tip. In a colour magnitude diagram, that tip appears as a sharp cut-off in brightness, which can be measured in nearby galaxies. TRGB stars live in older, less dusty populations, reducing extinction and crowding issues. The method still depends on calibration and population effects, and its current H0 results sit between the extremes. On screen, the TRGB method looks like archaeology. Instead of a few bright beacons, you see a dense field of faint stars, each one a data point. The camera can trace a colour, magnitude diagram where a cliff edge appears, the sudden drop where stars cannot be brighter without igniting helium. That cliff becomes a ruler. It is less dramatic than a supernova, but it is steady, and steadiness is valuable in a controversy. Water megamasers provide geometric distances through orbital dynamics, and they are among the cleanest measurements in the field. In certain active galaxies, massive spots trace a rotating disk around a central black hole, emitting intense microwave radiation. Measuring velocities and angular accelerations yields a direct distance through simple geometry and Newtonian dynamics, with relativistic corrections where needed. The method is clean physics, but usable systems are rare and hard to find. Nature does not provide many perfectly oriented mesa disks. Visually, masses are invisible to the eye, so the imagery becomes data-driven. You see a thin disk traced by points, each point a mesa spot with a measured velocity. A rotation curve emerges, and the disk's angular structure converts into a distance. It is a cosmic version of measuring the solar system by tracking planetary orbits. When it works, it feels almost unfairly direct. Standard sirens use gravitational waves as distance indicators, and they bring an entirely different messenger into the debate. The waveform encodes an absolute luminosity distance without a cosmic distance ladder, because the amplitude and frequency evolution carry the scale. If an electromagnetic counterpart identifies the host galaxy, redshift provides the velocity side. The promise is enormous, because it bypasses many astrophysical calibrations, but current event numbers are small, and systematics in counterpart identification remain. Even without counterparts, statistical associations with galaxy catalogues can still provide constraints, though with broader uncertainties. Visually, standard sirens invite a new aesthetic. A chirp becomes a rising tone, a waveform sweeping upward as two compact objects spiral together. Detectors on Earth, LIGO, Virgo, Cagra, appear as quiet instruments listening to space-time itself. Then a pinpoint of light may appear in a galaxy, tying the gravitational signal to a redshift. It is a rare moment when the universe speaks in two languages at once. Each cross-check is a partial judge, and none yet ends the case alone, because each carries its own modelling burdens. Together they form a convergence test for the ladder and the CMB, and convergence is what cosmologists crave. If they cluster near one side, the other side must yield. If they scatter, the universe may be telling us the problem is more subtle. Subtlety is not comforting, but it is often where truth hides. Now the chapter tightens around what each method truly measures, because the tension is partly semantic. The ladder measures local distances and velocities, then reads H0 directly from the slope, with minimal cosmological assumptions. The CMB measures early universe conditions, then infers H0 through a model that links epochs across nearly 14 billion years. The tension is therefore not only about measurement, it is about whether the link between epochs is fully understood. Are we correctly translating a primordial snapshot into a present-day speed? This is where the sound horizon becomes more than a technical term. It is the bridge between the early universe and today's distance scale, and bridges can fail in two ways. The measurements on either side can be wrong, or the engineering assumptions can be incomplete. LCDM has been an extraordinarily successful bridge, explaining the CMB, large-scale structure, and the accelerating expansion. Yet success can conceal fragility, because a model can fit many things while still missing a small component. The Hubble tension asks whether that missing component is now being revealed. Early dark energy is one leading new physics candidate, and it is attractive because it targets the sound horizon directly. It adds a brief energy component before recombination, increasing the expansion rate then, but fading away later. Faster early expansion shrinks the sound horizon, so the same observed CMB angles imply a higher H0 today. It can reconcile the numbers in principle, and it does so by changing the ruler rather than the late universe. In narrative terms, it changes the prologue, not the ending. To picture early dark energy, imagine a hidden actor stepping onto the stage for a short scene. For a narrow window of cosmic time, this component contributes a few % of the total energy density, pushing the expansion faster. Then it dilutes or transitions, leaving the later universe looking almost standard. The trick is timing and amplitude. Too much, too long, and the CMB peaks shift in ways we would immediately notice. Early dark energy introduces trade-offs that show up elsewhere, and those trade-offs are where many models struggle. It can alter the growth of structure, affecting galaxy clustering and weak lensing, because the expansion rate influences how matter collapses. It can shift the CMB peak structure and damping tail, which are measured with high precision. Many early dark energy models fit some datasets while straining others, especially when large-scale structure constraints are included. The universe keeps receipts, and it demands consistency. Extra-relativistic species is another route, often parameterized as NEF, and it is conceptually simple. Additional light particles increase the radiation density in the early universe, acting like extra neutrinos or other weakly interacting species. That changes the expansion rate before recombination and can shrink the sound horizon. A smaller sound horizon again pushes inferred H0 upward. The appeal is that particle physics already hints at hidden sectors, so the idea feels plausible. NEF is constrained by the CMB damping tail and by primordial nucleosynthesis, which is a remarkable cross-era connection. More radiation changes the diffusion length of photons, affecting small-scale CMB anisotropies, and those small scales are measured in detail. It also changes the freeze-out conditions for light element abundances, especially helium and deuterium, because the expansion rate sets reaction timing. The allowed room for extra species is limited, so the fix is not free. Every added particle must pass two ancient tests, the first few minutes and the first few 100,000 years. Evolving dark energy shifts the late-time expansion curve instead of early physics, and it asks a different question. If dark energy is not a cosmological constant, its equation of state could vary with time, changing how acceleration turns on. That can change distances to supernovae and BOO, and it can change how H0 is inferred from combined datasets. The challenge is that supernovae, BAO, and CMB together already restrict many variations tightly. The data prefer a dark energy that behaves very close to a constant, at least within current precision. Modified gravity changes how matter and spacetime respond, altering both expansion and structure growth, and it is often motivated by deeper theoretical puzzles. Some models can mimic LCDM in the background expansion while changing growth rates, which can be tested with galaxy clustering and lensing. Others change the relation between lensing and clustering, which can be tested with weak lensing surveys and redshift space distortions. The difficulty is avoiding conflicts with solar system tests, gravitational wave propagation constraints, and the consistency between multiple cosmological probes. Gravity is tightly policed, from planetary orbits to merging neutron stars. These proposals share a theme, and it is the theme of constrained freedom. They can move H0, but they often move other observables at the same time. Cosmology is over-constrained, so every new dial pulls on several gauges. A model that fixes H0 but breaks the CMB damping tail or distorts BAO is not a solution. The universe allows only certain kinds of deviations, and it reveals them through correlations. The alternative is that the ladder contains hidden systematics, and systematics are often more devious than theory. Cepheid metallicity effects could shift the period, luminosity relation in different host environments, because metal content changes opacity and temperature structure. Selection bias could favour brighter supernovae in ways that correlate with host properties, especially when surveys have detection thresholds. Population evolution could change type IA standardization with redshift, introducing subtle drifts. None of these effects needs to be large to matter, they only need to be coherent. Calibration is the most dangerous place for a small error to hide, because calibration is the foundation everyone stands on. Parallax 0 points at microarc second levels can move the entire ladder, and the correction must be stable across magnitude and colour. Photometric 0 points across instruments can introduce correlated offsets, especially when filters differ and transformations are imperfect. Even the definition of which stars are included can bias the mean brightness, if blending is not fully corrected. The more precise the measurement, the more painful the calibration. Webb's role is therefore double-edged because it can confirm the ladder or destabilize it. If Webb confirms the ladder calibration with cleaner infrared data, it strengthens the case that the local value is real. If Webb reveals a systematic shift, it could lower H0 and ease the tension. Early results have tightened the ladder and tested crowding, but they have not produced a collapse of the discrepancy. The story remains one of narrowing uncertainty rather than dramatic resolution. Now connect back to Webb's earlier anomalies, because the themes rhyme and the timeline is shared. If early galaxies are more massive, more organized, or more metal-rich than expected, then early-time astrophysics, or early-time physics, may be different. A changed early expansion history could alter inferred ages at high redshift, shifting how quickly structure must form. A changed sound horizon could alter how we map early structure to today's parameters, subtly reshaping the cosmic ledger. The same model that fixes H0 might also change the inferred pace of early assembly. Even if the anomalies are astrophysical, they still stress the same timeline, and that stress is informative. Rapid star formation and early enrichment demand efficient cooling, feedback, and gas inflow. Those processes depend on the density field and on the time available, both tied to cosmology. If the universe is younger at a given redshift, early galaxies must do more, faster, with less time. If the universe is older, the pressure eases, but other constraints tighten. The Hubble tension becomes a bridge between Webb's galaxy surprises and the universe's global parameters, and bridges invite traffic in both directions. Galaxy formation models rely on cosmological time and density evolution, while cosmological inference relies on how matter clusters and emits light. When Webb shows a galaxy that looks too mature too early, it is not automatically new physics. Yet it is a clue that our timeline assumptions matter, and H0 is a key part of that timeline. Narrative escalation. The tension is no longer a technical dispute about error bars, because it touches the coherence of the entire cosmic story. It is a fork in the universe's biography, implying different ages, different growth histories, and different fates. A higher H0 implies a younger universe and faster recent expansion, which compresses the schedule for early structure formation. A lower H0 implies an older universe and a different pacing for how matter clumps and galaxies mature. The same sky, two biographies, both cannot be fully right. The stakes extend beyond one number, because H0 is a scale setter that quietly enters almost every conversion. H0 sets the scale for distances, which sets luminosities, which sets masses, which sets inferred star formation rates. It sets the conversion from redshift to time, which sets when galaxies and black holes had to assemble. It even sets how we interpret the earliest light Webb collects, because that light is mapped onto a timeline. When H0 shifts, the meaning of early shifts with it. There is also a philosophical sting here, and it is worth lingering on. Cosmology has long relied on the idea that the universe is describable by a small set of parameters. LCDM, with its handful of numbers, has been a triumph of that approach. The Hubble tension asks whether that triumph is complete, or whether a missing term has been hiding in plain sight. Are we watching the first crack in a simple model, or the last stubborn systematic in a complex measurement? So the chapter ends with a controlled uncertainty, because the evidence points to a narrowing set of possibilities. Either the early universe model needs a new ingredient, carefully tuned to preserve CMB success, while shifting the sound horizon, or the local universe hides a systematic that has survived multiple independent checks, hiding in calibration, selection, or astrophysical complexity. The universe is forcing a choice, and every new dataset narrows the escape routes. That narrowing is what makes the story tense. The story began with Webb looking backward, yet it ends by looking forward, because cosmology is always a two-sided mirror. In the deep fields, faint smudges resolve into structured galaxies, disks, bulges, and knots of star formation, appearing earlier than our simplest timelines preferred. Early galaxies looked heavy, organized, and chemically awake sooner than expected, as if the universe learned to build quickly in the dark. The Hubble tension suggested our cosmic clock might be slightly misset, with local measurements ticking faster than the early universe inference. Together they force a deeper question about the engine of acceleration, and about how confidently we translate redshift into time. Dark energy entered cosmology as a surprise, not a preference, and the shock still echoes through the field's history. In the late 1990s, two teams used Type-wire supernovae as calibrated beacons, because these explosions reached nearly uniform peak brightness after empirical corrections. They looked dimmer than a decelerating universe predicted, even after accounting for dust and the known evolution of stellar populations. The simplest reading was that expansion is speeding up, not slowing down, and that the universe is not merely coasting. That result turned the universe from a slowing explosion into an accelerating one, and it forced a rethinking of what empty space contributes. Visually, the discovery is almost quiet, a scatter plot of distance versus redshift, with points drifting above the expected curve. Yet inside that gentle offset sits a radical claim. Spacetime's expansion rate is changing sign in its second derivative. Acceleration implies a component with negative pressure in general relativity, which is counterintuitive in plain language, because pressure usually feels like pushing outward. Energy density alone does not determine gravity's sign in an expanding universe, because Einstein's equations couple geometry to the full stress energy content. Pressure contributes to the stress energy that shapes spacetime, and it does so in a way that matters most when the universe is smooth on large scales. If pressure is sufficiently negative, it drives repulsion on cosmic scales, not by pushing objects through space, but by changing how space itself evolves. We summarize that behavior with one number, the equation of state parameter W, because cosmology often compresses complexity into a single symbol. It is defined as pressure divided by energy density for the dark energy component, a ratio that tells us how that component redshifts as the universe expands. If W equals -1, the density stays constant as space expands, so the total amount of dark energy grows with volume. That special case is the cosmological constant, the lambda in LCDM, and it behaves like a fixed energy density of the vacuum. A cosmological constant is not a force field that thins out with distance, and it does not clump into halos the way matter does. It is a property of spacetime that does not dilute as the universe grows, so its relative importance increases as everything else spreads out. Matter thins as volume increases, and radiation thins even faster because each photon is also redshifted, losing energy as wavelengths stretch. A constant dark energy eventually dominates everything else, not by growing stronger, but by refusing to fade. This is where the fate of the universe becomes a measurement problem, and the drama becomes statistical rather than cinematic. The long-term outcome depends on the true expansion history, not our intuition, because intuition evolved for falling apples and burning fires. It depends on whether W is exactly -1, slightly above it or below it, and the sign of that deviation matters more than its smallness. It also depends on whether W changes with time, because a gentle drift today can become decisive over trillions of years. If W is near -1 and stays there, the universe accelerates forever, and the expansion approaches an exponential form. Distances between unbound galaxies grow faster than light can cross them, which sounds like a violation until you remember what relativity actually forbids. That does not violate relativity, because space itself expands, and no galaxy locally outruns a beam of light in its own neighbourhood. It means horizons form, and information becomes unreachable, as if the observable universe slowly shutters. In visuals, the horizon is a fading boundary rather than a wall. Galaxies redden, dim, and then slip beyond a limit where their photons never arrive. In this heat-death scenario, the universe does not end in a bang, and it does not end with a single closing frame. It ends in dilution, isolation, and a slow loss of usable energy, as gradients flatten and opportunities for work evaporate. Galaxy groups remain bound, but everything beyond them drifts out of causal contact, leaving island universes in an ocean of expanding darkness. The night sky empties, not because objects vanish, but because light cannot arrive, and because the cosmic background itself cools toward invisibility. Star formation fades because gas becomes scarce and locked into long-lived remnants, and because the interstellar medium becomes harder to compress. In the present universe, cold molecular clouds collapse under gravity, but in the far future the raw material is steadily consumed or expelled. Massive stars die quickly, leaving neutron stars and black holes, and their supernova feedback stirs and heats the remaining gas. Smaller stars burn for trillions of years, then cool into dark dwarfs, radiating faintly in infrared before fading toward near black. The universe grows older and darker without a single dramatic moment, and the most common light becomes a low, cold whisper. On even longer timescales, black holes dominate the mass budget of bound structures because they are the most durable repositories of mass energy. They merge in slow gravitational dances, accrete what little matter remains, and then slowly lose mass through Hawking radiation, a quantum effect near the event horizon. That evaporation is unimaginably slow for stellar and supermassive black holes, with lifetimes that dwarf the current age of the cosmos by absurd factors. Yet in an eternal acceleration picture, even black holes are temporary, and even the darkest objects have an expiration date. Heat death is therefore not a single event, but a trajectory, and the word death is a metaphor for thermodynamic exhaustion. Entropy increases, temperature differences flatten, and free energy becomes harder to extract because work requires contrasts. The cosmos approaches a thin, cold equilibrium where particles are sparse and interactions are rare. It is an ending defined by what cannot happen anymore, and by the silence left when complexity can no longer be maintained. But heat death is only one branch, and it rests on a specific assumption that might be almost right without being exactly right. It assumes dark energy behaves like a constant vacuum energy, with W fixed at -1 across cosmic time. If W is not -1, the future can change qualitatively, even if the deviation is small enough to hide inside today's error bars. A small deviation today can compound over trillions of years because cosmic expansion integrates tiny differences into enormous separations. If W is less than -1, dark energy becomes phantom energy, a name that signals how strange the required physics can be. In that case, its density increases as the universe expands, which reverses the usual expectation that expansion dilutes everything. Acceleration then intensifies without bound, rather than approaching a steady exponential, and the scale factor can diverge in finite time. The expansion rate itself runs away, and the distance between any two unbound points grows with a kind of mathematical urgency. The runaway leads to the big rip, and the sequence is ordered by binding strength, like a cosmic unzipping. First, galaxy clusters lose their gravitational binding as expansion overwhelms attraction, and the tenuous filaments between them snap. Then individual galaxies are pulled apart as the background stretching outpaces their internal gravity, and stellar orbits no longer close. Later, solar systems unbind, and planets drift away from their stars, with night skies that change on human-like timescales if the rip is close enough. Near the end, the story becomes almost surreal, but it follows from the same equations that describe today's acceleration. In the most vivid visualization, you watch a spiral galaxy smear outward, its arms loosening as if gravity's grip has weakened, even though gravity itself has not changed locally. Tidal expansion forces grow so large that they can overcome molecular bonds, and chemistry becomes impossible because electrons can no longer remain attached. In the most extreme versions, even atoms and nuclei are torn apart, and matter dissolves into a hot, chaotic bath. The universe ends not by cooling, but by being shredded, with the final moments defined by disassembly rather than exhaustion. Phantom energy is not just a different number, it is a different kind of physics, and it pushes against the guardrails that make theories sensible. It often violates energy conditions that keep theories stable and causal, conditions that in plain terms prevent negative energy runaway behavior. It can imply negative kinetic energy and quantum instabilities, where the vacuum can decay into particles without a flaw. That does not prove it is impossible, because nature is not obligated to respect our aesthetic preferences, but it raises the bar for believing it, and it demands a consistent microphysical model rather than a convenient fit. Current observations do not require W below -1, but they allow small excursions, especially when datasets are combined in different ways. Some datasets even drift slightly into phantom territory depending on priors and combinations, which is a reminder that inference is not the same as direct measurement. The uncertainty is not an invitation to panic, it is a reminder of how hard the measurement is and how many subtle calibrations sit underneath it. The far future hinges on a parameter we still constrain at the percent level, and percent level ignorance can become destiny on trillion-year baselines. The third branch is a reversal, the big crunch, and it sounds like a return to older cosmology, when matter density seemed destined to halt expansion. In a crunch, expansion slows, stops, and then turns into contraction, so the scale factor reverses direction like a thrown ball reaching its apex. Galaxies approach, temperatures rise, and the universe ends in a hot, dense collapse, with radiation blue shifting as wavelengths compress. It is the mirror image of a Big Bang, though not necessarily identical, because the contents and structures at the end are not the same as at the beginning. A crunch requires that acceleration is temporary or illusory, which means dark energy cannot behave like a constant forever. Dark energy could evolve with time, decreasing in density and losing dominance, so matter and curvature regain influence. It could even change sign, becoming effectively attractive, turning the cosmic push into a pull, or gravity itself could behave differently on the larger scales, altering the balance without contradicting local tests, which are far easier to satisfy. Each route demands evidence, because each route rewrites the late-time rules. Cyclic possibilities build on that idea, where a crunch becomes a bounce, and the end becomes a new beginning. In some models, contraction triggers new physics that avoids a singularity, perhaps through quantum gravity effects or exotic stress energy that becomes important at high density. The universe could re-expand, producing repeated epochs, with memory erased or partially preserved depending on the mechanism. These ideas are speculative, but they show how sensitive destiny is to dark energy's nature and to the assumptions hidden in our equations. What evidence would make a crunch plausible, beyond a philosophical preference for symmetry? We would need clear signs that W differs from -1 and evolves with redshift, not merely a constant offset. We would need a measured trend that dark energy weakens, not just statistical noise that wanders with sample selection. We would also need consistency with structure growth in the CMB, because any change echoes across time, altering how galaxies cluster and how potentials evolve. A crunch is not just a late-time story, because the universe keeps receipts in its large-scale structure. Right now, the data make a crunch difficult but not impossible, and the phrase, "not impossible," is doing careful scientific work. Supernovae and BAO generally favour an accelerating universe today, with distances that match a component close to W equals -1. The CMB anchors the early universe geometry under a model that assumes dark energy is simple, and that assumption is both powerful and dangerous. Yet the Hubble tension reminds us that the link between early and late may still be incomplete, and that the ruler we use might be slightly miscalibrated by missing physics. This is where the measurement toolkit becomes the plot, because the ending is hidden inside how we build the distance-redshift relation. BAO provides a standard ruler tied to the sound horizon, the imprint of pressure waves in the early plasma that froze into the galaxy distribution. Supernovae provide relative distances across cosmic time, mapping how brightness dims with expansion, and serving as a ladder rung between nearby and far away. The CMB provides a high redshift anchor and a model-dependent inference of parameters, because its peaks encode the physics of the early universe with exquisite precision. Combine them, and we constrain W and its evolution, but we also inherit each method's assumptions. Many analyses use a simple form, W0 plus way, to capture slow changes, because it is flexible enough to test drift without becoming unconstrained. Even if W is near -1 today, we could allow drift over time, and that drift can change the long arc of expansion. Subtle evolution can be invisible in current data, yet decisive over cosmic futures, because the integral of the expansion rate is what sets horizons. Precision is improving, but precision does not guarantee closure, because systematic errors can shrink more slowly than statistical ones. Systematics can masquerade as evolution, and evolution can masquerade as systematics, which is why cosmologists obsess over calibration pipelines. Dust selection effects and population drift affect supernova distances, especially when comparing nearby events to those in younger, lower metallicity galaxies. Nonlinear structure and galaxy bias affect BAO reconstruction, because galaxies are not perfect traces of the underlying matter field. Even the act of selecting targets can tilt the inferred universe, and the tilt can look like new physics. The CMB adds its own conditionality, because it infers late-time parameters through an assumed model, and the inference is only as honest as the model family. If early universe physics differs, the inferred ruler changes, and a small change in the sound horizon can ripple into H0 and W. That is why the Hubble tension matters for destiny, even though it sounds like a local dispute about kilometers per second. It hints that our expansion history may not be fully captured by LCDM, and that the clean separation between early and late might be an illusion. Now tie back to Webb's early universe surprises, because they are not separate mysteries scattered across different chapters. Early mass assembly, early metals, and oversized black holes all press on the same timeline, asking whether the universe built complexity faster than expected. They ask whether structure grew faster, or whether we misread the light through dust, emission lines, and lensing magnification. They also ask whether the background expansion history is slightly different, because the conversion from redshift to cosmic age is model dependent. When we say this galaxy is too old, we are really saying our clock model makes it too old. If the universe expanded differently in its first billion years, ages at high redshift shift, and the pressure on early galaxy formation can ease. A small change in H0 or in early dark energy can move the conversion from redshift to time, because the early expansion rate sets how quickly the universe cools and structures grow. That can ease or worsen the pressure on early galaxy formation, depending on the direction of change and its consistency with other probes. The same parameter that sets the future also sets the past, which is why destiny and archaeology are entangled. Webb's data also test the astrophysical side of the model, and that side is where many apparent anomalies are born. Stellar masses depend on assumptions about star formation histories and the initial mass function, which determines how many massive stars formed compared to small ones. Metallicity depends on photoionization modeling and extreme radiation fields, because emission lines respond to temperature, density, and ionizing spectra. Black hole masses depend on virial calibrations and selection bias, because we infer mass from line widths and luminosities through relationships built in the nearby universe. Each inference is a chain, and Webb is tugging on several links at once. Some Webb anomalies have already softened with spectroscopy and better modeling, which is what healthy science looks like in real time. Photometric redshift interlopers have been reclassified, because a few strong lines can mimic a high redshift color break. Emission line contamination has reduced inferred masses in some cases, because broadband filters can be flooded by nebular emission from intense star formation. Host galaxy light decomposition has improved black hole to bulge estimates, separating glare from structure with sharper imaging. The early universe is still extreme, but it is becoming less mysterious as the data become less ambiguous. Yet a stubborn residue remains, and it is scientifically valuable precisely because it resists easy cleanup. Even if none of it breaks LCDM, it marks where the model is least protected, where priors do the most work. It highlights the places where assumptions meet data at the edge of sensitivity, where one calibration choice can flip a conclusion. It tells us where the next % improvement will matter most, and where new surveys should spend their limited time. So does Webb break cosmology, in the dramatic sense of overturning the standard picture overnight. Not outright, and not alone, because cosmology rarely collapses from a single observation. It does something more subtle and more important, and the subtlety is the point. It forces us to admit that our map is conditional, and our confidence rests on linked inferences, each one vulnerable to hidden correlations. When the map is stretched to its limits, the seams become visible, and Webb has illuminated those seams. LCDM remains a remarkably successful compression of the universe, a minimal model that explains an astonishing range of data with a small set of parameters. It explains the CMB peaks, large-scale structure, and the broad history of expansion, and it predicts patterns that were later observed. But its key components are still placeholders with names, which is both its strength and its discomfort. Dark matter is inferred from gravity, not identified in the laboratory, despite decades of searches. Dark energy is inferred from acceleration, not understood in microphysics, and the cosmological constant problem remains a profound mismatch between theory and observation. The central question returns in its final form, and it is sharper now because the data are sharper. Are Webb's early universe discoveries real cracks in the standard model, pointing to missing physics in the expansion history or in gravity? Or are they telling us we have been misreading the oldest light, the growth of galaxies, and the selection effects of deep surveys? The honest answer is that both options remain open, and the boundary is now measurable rather than rhetorical. What would it take for a deviation in W to become a discovery rather than a fluctuation, and how would we recognize it in time? If the anomalies resolve, the resolution will still teach us something, because improved understanding is not a consolation prize. It will refine stellar population models under extreme conditions, where metallicity is low and radiation fields are hard. It will improve lensing and selection corrections in deep fields so that rare bright objects are not mistaken for typical ones. It will tighten the distance ladder and clarify whether 80 is a systematic or a signal, which feeds directly back into dark energy constraints. Even a no new physics ending is still a better measurement of reality. If the anomalies persist, they point toward new ingredients, but the ingredients are still variations on themes already in play. Dark energy might not be a constant, and you might drift with time, subtly reshaping the expansion history without announcing itself loudly. The early universe might contain additional energy components that shrink the sound horizon, shifting the CMB inferred ruler and easing the Hubble tension. Gravity might deviate from general relativity on the larger scales while hiding locally, changing how acceleration is interpreted. Each possibility is constrained, but none is yet eliminated, and that is why the chapter's ending remains conditional. Each possibility changes the ending, and the endings are not just metaphors but mathematical attractors. A true cosmological constant points toward heat death and endless horizons, with an ever-expanding gulf between island galaxies. Phantom behavior points toward a big rip with a timetable that could be finite, and with a final sequence written by binding energies. Evolving dark energy that fades could reopen the door to a slowdown, and in extreme cases a crunch, returning the universe toward a dense finale. The same W that fits today's data decides whether the far future is quiet, violent, or cyclical. The unsettling part is that these endings are not philosophical, even though they sound like mythic choices. They're encoded in a function of redshift we can measure, if we can control our systematics and broaden our baselines. The universe's fate is a parameter estimation problem, and the plot twist is that the protagonist is an error bar. Our descendants may learn the ending by reducing uncertainties, and by cross-checking methods that fail in different ways. When the final answer arrives, it may come as a small shift in a best-fit line. This is the final mysterious beat, and it is grounded in what Webb actually did, which was to expand the domain where our models must work. Webb did not just show us early galaxies, it exposed how much interpretation sits between photons and conclusions, and how fragile some inferences become at the edge. It widened the frontier of uncertainty, and it made that uncertainty productive, because productive uncertainty tells you where to look next. The universe may be far larger in scale, in complexity, and in possibility than our equations currently capture, and the gap between them is where discovery lives. We end where we began, with the oldest light in a new eye, and with the sense that the universe is still withholding its simplest explanation. The first deep look did not simply confirm our best story of creation, even when it supported many of its broad strokes. It revealed pressure points where the timeline, the growth of structure, and the expansion history strain against each other, and where small changes could reconcile the picture. The map still works, but the margins are fraying, and the fraying is a clue rather than a failure. Closing transition. The next observations will decide whether today's cracks become tomorrow's rewrite, through deeper fields, larger surveys, gravitational waves, and the telescopes that follow Webb. Webb set out to photograph the cosmic dawn, yet it returned a busier, brighter skyline than our forecasts allowed. Across deep fields, black hole nurseries, and oxygen-rich gas only a few 100 million years after the beginning, we kept meeting the same unease. The early universe looks too productive, and each chapter led to the same hinge point. Our conclusions depend on how we turn photons into distances, ages, and masses, and on how confidently we know the expansion history. We followed that hinge through the cosmic ruler, where redshift becomes time only after we choose a model, and where distance itself splits into competing definitions that are easy to confuse. We traced the inference chain that can inflate a galaxy, photometric redshifts that can be fooled, emission lines that can masquerade as starlight, dust and lensing that can brighten a source, and assumptions about stellar populations that can quietly double a mass. Yet even after spectroscopy trims the most extreme claims, a stubborn remainder persists. Compact galaxies that seem organized, black holes that seem ahead of their hosts, and chemistry that suggests stars ignited earlier or mixed their ashes faster than we expected. Then the story widened, because the Hubble tension is not just a disagreement about today, it reshapes the clock we use for yesterday. If the universe expands a little faster or slower than we think, the first billion years stretch or compress, changing how impossible too early really is. And beyond that sits the deepest stake, because the same expansion history that times cosmic dawn also forecasts cosmic fate, whether we drift toward heat death, tear apart in a rip, or someday reverse. So Webb's first revelations do not simply add detail to a familiar timeline, they stress test the scaffolding beneath it. They force us to ask whether nature built faster than our simulations allow, or whether our measurements, calibrations, and priors have been quietly steering the story. Either way, the lesson is the same. The universe is vast not only in size, but in the number of ways it can surprise us. Back at the beginning, we asked whether Webb had found real cracks in the standard model, or whether we were misreading the oldest light. The earned answer is more unsettling. The cracks may be in the cosmos, or in our translation of light into history, and Webb is showing us exactly where to press. In the end, space is not merely an emptiness measured in billions of light years, it is a living archive whose pages can be misfiled, mistranslated, or rewritten by new evidence. Webb has not closed the book on cosmology. It has made the margins wider and reminded us that the darkest distance is the one between what we see and what we think it means. Stay with the data as it sharpens, because the next spectra, the next calibration, and the next survey may decide whether we need better astrophysics or a deeper physics.